An object moving at over 58 kilometers per second crossed the inner boundary of the solar system, too fast to belong here, too intact to ignore. The timing matters because this is the final observation window before solar glare blinds ground instruments for 14 weeks, forcing astronomers to choose which mysteries get time and which are left to drift unanswered. Telescopes designed for galaxies billions of light-years away now pivot towards something passing between Mars and Jupiter, racing against geometry and bureaucracy. Spectral analysis shows simultaneous markers of extreme cryogenic preservation and high-temperature surface restructuring, a contradiction no known comet model fully explains. Water ice signatures appear alongside vitrified silicates, compounds that should never coexist on a single surface. The chemistry suggests exposure to temperatures below -260 degrees Celsius, followed by localized heating intense enough to melt rock. The object is now known as 3I Atlas, only the third confirmed interstellar visitor ever detected. But unlike its predecessors, this one carries scars, etched by deep cold, then rewritten by heat. Before we go deeper, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding. Data arrives fragmented, observation time collapses under institutional backlog, and the questions accumulate faster than answers. As governments delay telescope funding and observation time collapses under backlog, data continues to arrive, fragmented, incomplete, but troublingly consistent. Each measurement confirms what shouldn't be possible. Each model breaks against what we observe. This is 3I Atlas. Chapter 1. September 14th, 2025, The Cold That Preserved at T. The discovery didn't announce itself with drama. On September 14, 25, at 3:47 Universal Time, the Atlas Survey Telescope on Mauna Loa logged a transient object moving 1.3 degrees across the sky in 6 hours. The automated system flagged it as unusual, not for brightness, but for velocity. Objects that move this fast through the inner solar system don't usually survive long enough to be catalogued. Within 18 hours, follow-up observations from Pan-STARRS confirmed the trajectory. The orbit was hyperbolic, not elliptical, not bound to the sun. The eccentricity measured 1.89, meaning this object was moving too fast to ever return. It had come from somewhere else. The Minor Planet Center issued a preliminary designation. Orbital reconstruction began immediately. When you trace an object's path backward through time, you're following gravitational breadcrumbs, planetary encounters, solar influences, the slow accumulation of perturbations. For objects born in our solar system, those breadcrumbs lead back to the Kuiper Belt, the Oort cloud, or the scattered disk beyond Neptune. For 3I Atlas, they led outward. The calculations placed its origin in interstellar space, traveling for at least 3 million years before encountering the sun's gravity well. During that time, it existed in conditions colder than anything naturally sustained within our planetary system. Temperatures below -260 degrees Celsius. Thermal energy so low that molecular motion nearly stops. This is the kind of cold that crystallizes methane into lattices harder than steel. The kind that locks water molecules into configurations that never melt. The kind that preserves. Infrared spectroscopy from the NASA Infrared Telescope facility on Mauna Kea revealed absorption lines corresponding to pristine water ice, carbon monoxide ice and methanol, volatile compounds that sublimate rapidly under even weak sunlight. For these materials to survive intact, the object must have spent eons shielded from stellar radiation, drifting through the vast empty spaces between star systems. But here's the first anomaly. Most comets, even those originating in the distant Oort cloud, show signs of thermal degradation. Cosmic rays erode surfaces over millennia. Collisions pulverize structure. Interstellar dust impacts at relative velocities high enough to vaporize rock. Even in deep space, nothing stays pristine forever. 3I Atlas did. Dr. Elena Mora, a planetary chemist at the European Southern Observatory, was among the first to notice the discrepancy. She compared the spectral profiles of 3I Atlas to those of long-period comets that had spent comparable time in cold storage. The volatiles on 3I Atlas were more intact. The ice-to-dust ratio was higher. The surface showed less evidence of space weathering. "It's not that it survived the cold," she said during an interview for a preprint commentary. "It's that it survived too well." Theoretical models predict that objects traveling through interstellar space should accumulate a mantle of irradiated organic material, darkened, chemically altered, thermally disrupted. This mantle acts as insulation, but also as evidence of exposure. 3. Atlas showed minimal mantling. Its surface reflected light, almost as if freshly exposed. 2 explanations emerged. The first. 3I Atlas originated in an environment even colder and more isolated than typical interstellar space, perhaps ejected from a rogue planetary system or born in a molecular cloud so dense that radiation couldn't penetrate. This would place its formation in conditions we've never directly observed, but which theoretical astrophysics allows. The second explanation was quieter, shared in emails rather than press releases. If the object had been deliberately shielded, encased in something that later sublimated away, or positioned in a way that minimized exposure, it might explain the preservation. But invoking deliberate action requires evidence we didn't yet have. So the scientists focused on what they could measure. Spectroscopic resolution from the Gemini North Telescope identified specific isotopic ratios in the water ice, ratios that matched predictions for protostellar cloud condensation. The deuterium to hydrogen ratio was slightly elevated, consistent with formation in environments where temperatures approached absolute zero. This wasn't just cold. This was primordial cold, the kind that existed before stars ignited, when the universe was darker and emptier than we can easily imagine. The molecular bonds showed unusual stability. Methanol clathrates, cage structures where methanol molecules trap other volatiles, appeared intact despite millions of years of micrometeorite bombardment. The lattice spacing, measured through Raman spectroscopy, indicated minimal thermal disruption since formation. "This object is a time capsule," Dr. Mora noted in her published analysis. But time capsules usually degrade. This one didn't. The team calculated the expected sublimation rate as 3I Atlas approached the Sun. Even at distances beyond Jupiter's orbit, solar radiation should begin to erode surface ices. The predicted mass loss was approximately 0.3% per day at 5 astronomical units from the Sun, enough to produce a visible coma and tail. 3. Atlas produced almost none. The brightening curve, how an object's luminosity changes with distance from the Sun, remained nearly flat. Instead of the exponential increase expected from sublimating volatiles, the light curve showed linear growth, suggesting that reflected sunlight, not outgassing, dominated the signal. This was the behavior of a rocky asteroid, not an icy comet. But the spectroscopy insisted it was ice. The contradiction forced a recalibration. If the surface was icy but not actively sublimating, something was protecting it. A thin crust of refractory material, silicates, carbonaceous compounds, could act as insulation. But such crusts form through heating, through repeated solar approaches that bake volatiles inward and leave behind a hardened shell. 3I Atlas had never been heated. Not before now. The backtraced trajectory showed no close stellar encounters in the past 5 million years. No passage through stellar wind regions. No exposure to radiation environments energetic enough to drive crustal formation. The object should have been bare ice, not armored. Dr. Thomas Reinhardt, an orbital dynamicist at Heidelberg University, ran Monte Carlo simulations to test alternative formation scenarios. He modeled ejection from stellar systems with varying architectures, collision events in dense stellar nurseries, and radiative shielding by interstellar dust concentrations. None produced the exact conditions observed. "We keep finding ourselves backing into the same corner," he said during a video call with colleagues. "The object is too well preserved for its environment, and too well protected for its history." The phrase "too well" appeared in internal memos more frequently than anyone wanted to admit. Meanwhile, public attention remained minimal. Interstellar objects, while scientifically thrilling, don't generate the visceral engagement of Mars rovers or exoplanet imaging. The press releases were polite and subdued. Funding agencies noted the discovery, but allocated no emergency observation time. 3 Atlas was cataloged, measured, and filed. But the scientists couldn't let it go. Infrared data from the Spitzer Space Telescope archive, captured during its final operational months, was cross-referenced with the object's predicted position. The archive search returned nothing. 3 Atlas had been too faint, too far, or too recent to appear in earlier surveys. Its arrival was unannounced. This raised a procedural question. If interstellar objects arrive without warning, how many do we miss? Current detection networks cover only a fraction of the sky, prioritizing regions where near-Earth asteroids concentrate. Objects approaching from high ecliptic latitudes, above or below the plane of the solar system, often go unnoticed until they're already inbound. 3 Atlas had approached from 34 degrees above the ecliptic, a trajectory that avoided the densest observation zones until it was already inside Neptune's orbit. "We got lucky," admitted Dr. Yuki Tanaka, a survey astronomer with Atlas. "If it had been 10% dimmer, we'd have missed it entirely." The implications settled quietly into the community. If this was the third confirmed interstellar object, how many unconfirmed ones had passed through? How many more were currently inbound, invisible against the stellar background? As September closed, the initial excitement gave way to methodical analysis. Observatories scheduled follow-up time. Data pipelines filled with spectra, photometry curves, and astrometric positions. The object continued inward, sunlight strengthening, surface temperatures rising. And then, the second anomaly appeared. By September 28th, 3 Atlas had crossed 4.2 astronomical units from the Sun, roughly the distance of Jupiter's orbit. At this range, solar flux intensifies enough to drive sublimation in even well-insulated comets. The expected outgassing should have begun. It didn't. Instead, something else started to happen. Something no one had predicted. The surface was changing. Chapter 2, September 18, 2025. A solar system on a budget. 4 days after the initial detection, the scramble for observation time began. Telescope scheduling operates on a principle of scarcity. Every major observatory, ground-based or orbital, receives more proposals than it can accommodate. Time is allocated months in advance through competitive peer review. Requests are weighed by scientific merit, feasibility, and alignment with institutional priorities. Emergency overrides exist, but they require justification. 3 Atlas did not initially qualify as an emergency. On September 18th, Dr. Elena Mora submitted a request for 12 hours of observation time on the Very Large Telescope in Chile. Her proposal outlined spectroscopic analysis to determine chemical composition, isotopic ratios, and thermal properties. The science case was strong. The review committee acknowledged its merit. They also noted that Velte was already fully booked for the next 6 weeks, with observations of exoplanet atmospheres, gravitational lensing events, and a coordinated campaign studying supernova remnants in the Large Magellanic Cloud. Rescheduling would disrupt multiple teams and potentially compromise data that couldn't be recovered later. The committee offered a compromise: 4 hours of observation time during a gap caused by poor weather forecasting. If clouds cleared unexpectedly, 3 Atlas would get a window. If not, the request would roll to the next available slot. Dr. Mora accepted. Meanwhile, NASA's Infrared Telescope facility faced its own allocation conflicts. The facility, perched on Mauna Kea in Hawaii, operates as a community resource for planetary science. Time is divided between NASA-funded projects and guest investigators. September's schedule was dominated by observations of Jupiter's magnetosphere, Saturn's rings, and near-Earth asteroid thermal modeling for planetary defense purposes. Planetary defense, the effort to catalog and characterize asteroids that might threaten Earth, receives priority funding. This is understandable. Protecting civilization from impact events is a measurable, politically defensible goal. Studying distant interstellar visitors is not. Dr. Tanaka, who had initially detected 3 Atlas, requested 3 nights of infrared spectroscopy to track volatile composition as the object approached the Sun. The request was flagged as scientifically valuable but non-urgent. The committee allocated 1 night, contingent on completion of scheduled planetary defense observations. The pattern repeated across observatories worldwide. Requests were submitted, reviewed, and slotted into schedules already strained by competing demands. No single observation was denied outright, but no one received the time they wanted. This is the infrastructure problem that rarely makes headlines. We built telescopes capable of imaging galaxies at the edge of the observable universe, but we operate them on budgets that assume leisurely schedules and predictable targets. When something unexpected arrives, a supernova, a gravitational wave counterpart, an interstellar object, the system strains. Astronomers improvise. Dr. K. Mora coordinated with colleagues at the European Southern Observatory to share data from multiple instruments, stitching together partial observations into a composite profile. Dr. Tanaka negotiated with Pan-STARRS to prioritize 3A Atlas during routine survey sweeps, accepting lower resolution data in exchange for consistent coverage. The Hubble Space Telescope, arguably the most oversubscribed observatory in history, received a request for high-resolution imaging. The proposal argued that Hubble's sensitivity could resolve surface features invisible to ground-based instruments, potentially revealing structural asymmetries that would constrain formation models. The Space Telescope Science Institute, which manages Hubble's schedule, acknowledged the scientific importance. They also noted that Hubble was currently allocated to deep field surveys, stellar population studies, and critical observations of Kuiper belt objects during rare occultation events. 3I Atlas was added to the Targets of Opportunity list, a category reserved for transient phenomena that justify schedule interruptions. But to trigger an override, the object would need to exhibit something demonstrably extraordinary. At this point, it had not. It was simply an interstellar comet, well-preserved and curiously quiet, drifting inward toward a system that lacked the resources to study it properly. This is the unspoken tension in modern astronomy. We live in an era of unprecedented observational capability, telescopes spanning wavelengths from radio to gamma rays, instruments precise enough to detect exoplanet atmospheres and gravitational ripples in spacetime. But we lack the infrastructure to use these tools freely. Every observation competes with 100 others, each scientifically justified, each potentially transformative. The Vera C. Rubin Observatory, under construction in Chile, promises to change this. Once operational, it will survey the entire visible sky every few nights, automatically cataloging transient events and moving objects. It will detect interstellar visitors like 3I Atlas weeks earlier, providing time for coordinated follow-up. But Rubin won't reach full operations until late 2026. For now, we watch the sky with instruments designed for a slower universe. Meanwhile, on September 20th, a different bottleneck emerged. NASA's Deep Space Network, the array of radio antennas that communicate with interplanetary spacecraft, faced a scheduling conflict. The network operates 3 complexes, one in California, one in Spain, one in Australia. Together, they provide continuous coverage for missions across the solar system. But continuous coverage doesn't mean infinite bandwidth. On September 20th, the Mars Reconnaissance Orbiter required emergency downlink time to transmit high-priority imaging data from a suspected water seep site. The James Webb Space Telescope needed antenna time to relay commands for an updated observation sequence. The Voyager 2 probe, over 20 billion kilometers from Earth, was scheduled for its monthly health check. And Dr. Reinhardt wanted to use the Very Large Array in New Mexico to observe 3 Atlas in radio wavelengths. The VLA, a collection of 27 radio dishes arranged in a Y-shaped configuration, can detect faint radio emissions from cometary outgassing, solar-wind interactions, and magnetospheric effects. If 3I Atlas had even a weak ionized coma, the VLA could measure it. But the VLA shares scheduling with other priorities, including studies of distant quasars, pulsar timing arrays for gravitational wave detection, and observations supporting Mars atmospheric research. Reinhardt's request was approved for 6 hours, split across 2 nights, during periods when the array configuration aligned with 3 Atlas's position. The time was sufficient to detect strong signals, but not to perform detailed spectral analysis. We'll get a snapshot, Reinhardt said. Not a portrait. This became the theme of late September. Snapshots, fragments, composite images assembled from instruments never designed to work together. On September 22nd, the European Space Agency's Mars Express orbiter completed a trajectory adjustment that temporarily freed its high-gain antenna from Mars relay duties. ESA offered the antenna for radio occultation studies of 3E Atlas, a technique where radio waves pass through the object's coma and reveal density structure based on signal refraction. The opportunity lasted 4 hours. Dr. Mora assembled a team to coordinate observation timing, accounting for the object's motion, Earth's rotation, and the antenna's pointing constraints. The window was narrow, the geometry challenging, but the data would be invaluable. The observation succeeded. The results were puzzling. There was no detectable coma. Radio occultation requires a diffuse gas envelope to refract signals. 3 Atlas, despite being well within the sublimation zone for water ice, produced no measurable gas emission. The radio waves passed through cleanly, unrefracted. This shouldn't be possible, Mora told her team during a post-observation debrief. Either the surface isn't ice, or the ice isn't sublimating. Spectroscopy insisted it was ice. Observations insisted it wasn't outgassing. The data pipeline strained under the contradiction. On September 24th, NASA's Planetary Defense Coordination Office released a statement clarifying that 3I Atlas posed no impact threat to Earth. The trajectory was well constrained, the closest approach would occur at a safe distance, and the object's small size, estimated at roughly 400 meters in diameter, meant it couldn't cause global-scale damage even if it did collide. The statement was routine, precautionary, and reassuring. It also diverted public attention away from the more interesting questions. Why was the object so intact? Why wasn't it outgassing? What was protecting the surface? These questions didn't fit neatly into press releases. They required nuance, speculation, and an admission that we didn't yet understand what we were observing. Later that week, Dr. Tanaka received an email from the Atlas operations team. Automated surveys had detected 3 additional fast-moving objects in the past month, all on hyperbolic trajectories. None were bright enough for detailed follow-up. None triggered the level of interest that 3A Atlas had. But the frequency was higher than expected. Statistical models predict roughly 1 detectable interstellar object per year, given current survey coverage and sensitivity limits. 3 in a month suggested either a statistical fluctuation, unlikely but possible, or an increase in interstellar traffic through the inner solar system. We might be living through a peak, Tanaka speculated in a conference call. Or we're just now getting good enough to see what was always there. Neither explanation was comforting. As September closed, the observation campaigns continued. Data accumulated in archives, preprint servers filled with preliminary analyses, and email threads sprawled across continents. Coordination happened informally, through personal relationships and professional courtesy rather than institutional mandate. No one was in charge. No one had authority to redirect resources or override priorities. The system operated as it always had, distributed, competitive, and overwhelmed. And 3I Atlas continued inward, indifferent to the bureaucracy tracking it. The surface temperatures had risen above -200 degrees Celsius. Sunlight, still faint, was beginning to deposit energy faster than the object could radiate it away. Something was about to change. Chapter 3, September 22, 2025. Heat that should have destroyed it. Thermal modeling begins with first principles. When an object absorbs sunlight, its temperature rises until the energy radiated away balances the energy absorbed. For dark rocky asteroids, equilibrium temperatures at Jupiter's distance hover around -160 degrees Celsius. For icy comets with high albedo, temperatures remain lower, perhaps -180 degrees. 3I Atlas should have been warming according to these predictions. The models were straightforward. Input solar flux, surface albedo, thermal conductivity, and solve for temperature. The equations were undergraduate-level thermodynamics, verified across thousands of solar system objects. The models were also wrong. On September 22nd, thermal infrared observations from NASA's IRTF revealed surface temperatures 15 degrees higher than predicted. This might seem trivial. 15 degrees out of 200 is less than 8% deviation. But in planetary science, deviations of even a few percent indicate missing physics. Dr. Kenji Nakamura, a thermal modeler at Tokyo Institute of Technology, ran the calculations assuming different surface properties. He tested low albedo, high thermal inertia, variable surface roughness. None matched the observations. The object is retaining heat more efficiently than it should, he concluded in a preliminary report. Or it's generating heat internally. Internal heat generation requires an energy source. For comets, this typically means radioactive decay, potassium-40, thorium-232, uranium-238, isotopes that release heat as they disintegrate. But the quantities required to produce measurable surface warming would make the object far denser than observed. Its mass, estimated from trajectory perturbations, was consistent with porous ice, not dense rock. Another possibility: tidal heating. When objects pass close to massive bodies, gravitational gradients flex their interiors, converting mechanical energy to heat. But 3I Atlas was still beyond Jupiter's orbit, too distant for tidal forces to matter. The heat was coming from somewhere. On September 25th, spectroscopic data from Gemini North added another layer to the mystery. The infrared spectrum showed absorption features consistent with amorphous silicates, glassy minerals formed when molten rock cools rapidly. These signatures are common in volcanic ejecta, impact melt, and industrial ceramics. They are not common in comets. Amorphous silicates require temperatures above 1000 degrees Celsius to form. Crystalline structures melt, molecular bonds break, and the material freezes into a disordered glassy state. The process is fast, seconds to minutes, and leaves distinct spectral fingerprints. 3I Atlas had those fingerprints. "This is vitrification, Doctor," Mora said, staring at the spectral plot during a video meeting with colleagues. "The surface has been heat-treated." The team fell silent. Vitrification implies exposure to intense, localized heat, far beyond anything solar radiation could provide at interstellar distances. Either the object had passed close to a star before arriving here, or something on the object itself had generated the heat. Dr. Reinhard cross-referenced the trajectory data, checking for stellar encounters in the past 5 million years. The closest approach to any cataloged star occurred 2.1 million years ago, when 3I Atlas passed within 0.8 light-years of a red dwarf in the constellation Lynx. At that distance, stellar radiation would have been negligible, less than 1/10,000th the intensity of sunlight at Earth. Not enough to melt rock. Not enough to vitrify silicates. The heat had come from somewhere else. Dr. Nakamura proposed an alternative: impact heating. If 3I Atlas had collided with another object during its interstellar journey, the kinetic energy could have vaporized the impact site, melting rock and flash freezing it into glass. The glassy layer could then insulate the underlying ice, explaining both the thermal anomaly and the lack of outgassing. It was a reasonable hypothesis. Interstellar space contains dust grains, pebbles, and larger debris ejected from other star systems. Collisions, while rare, are inevitable over millions of years. But the spectral data didn't support a single impact site. The vitrified silicates were distributed across multiple regions, visible in spectra taken from different viewing angles. If impacts were responsible, the object had been struck repeatedly, in a pattern that seemed almost systematic. Random impacts produce random scars, Dr. Mora noted. This looks organized. The word hung in the air, unspoken in official reports, but present in every conversation. On September 28th, NASA's Jet Propulsion Laboratory released updated thermal models incorporating the vitrification layer. The models predicted that as 3I Atlas approached the Sun, the glassy coating would absorb solar energy more efficiently than bare ice, driving surface temperatures even higher. But instead of catastrophic sublimation, where the entire ice structure destabilizes and vaporizes, the glass layer would act as a thermal blanket, trapping heat beneath the surface. Subsurface ice would melt into liquid water, possibly creating pockets of pressurized fluid that could trigger localized eruptions. This was the behavior of cryovolcanism, observed on moons like Enceladus and Europa. But those moons have internal heat sources, tidal flexing from giant planets. 3. Atlas had none. The predictions included another troubling detail. If subsurface melting occurred, the object's rotation could redistribute mass unevenly, altering its spin state. Tumbling motion would follow, chaotic, unpredictable, and observable. Observers began monitoring rotation rates. Dr. Tanaka used pan-stars to measure brightness variations over time. A rotating object reflects sunlight differently depending on its orientation, producing a periodic light curve. For most asteroids and comets, these periods range from a few hours to a few days. 3. Atlas had a rotation period of 11.4 hours, stable and consistent over multiple observation cycles. The light curve showed a double-peaked structure, suggesting an elongated shape, perhaps twice as long as it was wide. But on September 30th, the period shifted. The rotation slowed to 11.7 hours, a change of 0.3 hours over 4 days. For a rigid body, this would require a significant torque, something capable of altering angular momentum. Outgassing could do this. Jets of sublimating gas act like tiny rocket engines, pushing against the surface and changing rotation rates. But 3I Atlas wasn't outgassing. Something inside is moving, Dr. Tanaka said during a team meeting. Mass is redistributing. The implications were immediate. If subsurface melting was redistributing internal mass, the object was thermally active in ways that natural models struggled to explain. Dr. Mora requested emergency time on the Atacama Large Millimeter Array in Chile, Alma, a network of 66 radio dishes designed to observe cold gas and dust in distant galaxies. ALMA can also detect millimeter wave emissions from cometary ice, mapping temperature gradients beneath the surface. The request was approved for 6 hours, during a gap in scheduled observations of protoplanetary disks. The data arrived on October 2nd. ALMA detected thermal emission consistent with subsurface temperatures, 30 degrees warmer than the surface, an inversion that should be impossible without an internal heat source. The emission was not uniform. It concentrated in 2 regions, roughly opposite each other, aligned with the object's rotation axis. This is deliberate, Doctor, Mora said quietly, reviewing the thermal maps. Heat is being directed. The team debated the phrasing. Deliberate, implied, intent, design, technology. A threshold they weren't ready to cross publicly. Dr. Reinhardt offered a softer interpretation. Directed doesn't require deliberation. Geological processes can channel heat. Tidal heating on Europa creates localized hotspots. Maybe 3 Atlas has a similar mechanism we don't understand yet. But Europa's heat comes from Jupiter's gravity. 3 Atlas had no such source. On October 4th, spectroscopic follow-up from the Keck Observatory revealed another anomaly. The vitrified silicates contained trace elements, nickel, chromium, titanium, in ratios inconsistent with chondritic meteorites or cometary dust. The ratios matched high-temperature industrial alloys, materials optimized for thermal endurance. These are refractory compounds, said Dr. Lena Sorensen, a geochemist consulting on the project, designed to withstand heat cycling. You'd use these in spacecraft heat shields or reactor linings. The room went quiet. Or, she added carefully, in natural environments we haven't encountered yet. Stellar atmospheres, protoplanetary collisions, extreme conditions could produce similar chemistry. No one was convinced. The probability estimates began to stack. Low albedo, despite ice composition, 1 in 50. Vitrified surface without stellar heating, 1 in 200. Organized thermal distribution, 1 in 400. Refractory trace elements, 1 in 100. Multiply the probabilities together, and the odds of all these features occurring naturally drop below 1 in 4 million. This is not proof of artificiality. Nature produces rare events constantly. Improbable outcomes are inevitable across the scale of the cosmos. But when improbabilities cluster on a single object, attention shifts. Dr. Mora drafted a confidential memo to the International Astronomical Union's Committee on Small Body Nomenclature. The memo outlined the observations, acknowledged the low probability of natural occurrence, and recommended elevated monitoring priority. The IU responded with cautious interest. They requested continued observation, but declined to issue public statements pending further data. The bureaucratic response was measured, appropriate, and frustrating. Meanwhile, 3I Atlas crossed 3.8 astronomical units from the Sun. Surface temperatures had risen above -150 degrees Celsius. The glassy coating continued to absorb solar energy, heating the interior. And the object continued to defy prediction. No coma. No tail. No outgassing. Just heat, accumulating in patterns that looked less random with every measurement. Cold had preserved it. Heat was reshaping it. And we had no idea what would happen next. Chapter 4. September 26, 2025. Starship waits, the object doesn't. On September 26, SpaceX conducted its 9th integrated flight test of the Starship launch system. The vehicle reached orbit successfully, deployed a test payload, and returned both stages to the launch site, a milestone in reusable heavy lift architecture. The success was celebrated across the aerospace industry. Starship represents the next generation of deep space capability, with payload capacities exceeding anything currently operational. The vehicle can carry 100 metric tons to low Earth orbit, refuel in space, and theoretically deliver significant mass to interplanetary trajectories. Theoretically. During a post-launch press conference, a reporter asked whether Starship could intercept 3I Atlas. Elon Musk, SpaceX's founder, paused before answering. "We could probably get there," he said. "But intercept trajectories are expensive. You're not just matching position, you're matching velocity, and this thing is moving fast. The orbital mechanics are unforgiving." 3. Atlas was traveling at 58 kilometers per second relative to the Sun. To intercept it, a spacecraft would need to accelerate to a similar velocity, then decelerate to match the object's speed and direction. The delta of A, the change in velocity required, was enormous, well beyond the capability of any existing mission profile. Dr. Reinhardt calculated the requirements during a sleepless night in late September. Assuming a direct Hohmann transfer from Earth orbit, the mission would require approximately 42 kilometers per second of delta VVI. Starship, fully fueled with orbital refueling, could deliver perhaps 8 kilometers per second. Even with gravitational assists from Venus and Earth, the numbers didn't close. "We need nuclear propulsion," Reinhardt told colleagues during a virtual meeting. "Or a massive multi-stage architecture we haven't built yet." Nuclear propulsion, specifically nuclear thermal or nuclear electric drives, has been studied for decades. The technology works in principle. Heat reaction mass using a nuclear reactor, expel it at high velocity, and achieve delta V far beyond chemical rockets. But no nuclear propulsion system has flown since the 1970s. Development timelines stretch across decades. Regulatory approvals require international coordination. Cost estimates run into tens of billions of dollars. For 3I Atlas, the timeline was months. On September 29th, NASA's Planetary Science Division convened an internal review to assess mission feasibility. The review included trajectory analysts, propulsion engineers, and program managers. The question wasn't whether an intercept was scientifically valuable. It clearly was, but whether it was achievable within available resources. The conclusion: not with current technology. A chemical propulsion mission could reach 3I Atlas's general vicinity, but couldn't match velocity. A flyby was possible, delivering perhaps minutes of close-range observation, as the spacecraft screamed past at tens of kilometers per second. The data return would be limited. A few images, spectra captured in passing, trajectory perturbations measured after the fact. Valuable, but not transformative. The review recommended continued ground-based observation instead. This is the frustration of interstellar object science. These visitors are rare, unpredictable, and fleeting. By the time we detect them, they're already departing. We watch through telescopes constrained by distance and geometry, while the objects themselves slip back into the void. Meanwhile, interplanetary mission planning moved forward on slower timelines. NASA's Dragonfly mission, a rotorcraft destined for Saturn's moon Titan, was scheduled for launch in 2028. The mission had been in development for years, its science objectives carefully defined, its instruments precisely calibrated for Titan's methane lakes and organic chemistry. Redirecting Dragonfly to intercept 3 Atlas would require abandoning Titan entirely, redesigning the spacecraft, and compressing years of engineering into months. The cost would be prohibitive. The risk would be extreme. And Dragonfly couldn't catch 3I Atlas anyway. The European Space Agency faced similar constraints. Their JUICE mission, Jupiter Icy Moons Explorer, had launched in April 2023 and was currently en route to Jupiter's moons. Its trajectory was fixed, its instruments optimized for Europa, Ganymede, and Callisto. JUICE could not be redirected. China's Space Agency had announced plans for an interstellar object intercept mission in the mid-2030s, but the design remained conceptual. Japan's Hayabusa program, renowned for sample return missions to asteroids, was focused on near-Earth targets with favorable trajectories. No one was positioned to chase 3 Atlas. On October 1st, Dr. Moore participated in a webinar hosted by the Planetary Society. The audience, astronomers, engineers, and space enthusiasts, asked whether an emergency mission could be assembled using commercial launch providers and off-the-shelf spacecraft components. Moore was diplomatic. In principle, yes. In practice, the integration time alone would exceed the opportunity window. By the time we built and tested the spacecraft, 3 Atlas would be gone. Oh, Hawaii. The sentiment was echoed across the community. We had tools capable of reaching distant planets, landing on comets, and sampling asteroids. But those tools required years of preparation, and 3 Atlas allowed us weeks. The public response was muted. Interstellar objects don't generate the emotional engagement of Mars rovers or crewed lunar missions. They're scientifically fascinating but visually abstract, distant points of light moving against the stellar background. No viral social media campaigns emerged demanding emergency funding. No political figures championed rapid mission development. The opportunity passed quietly, acknowledged, but not acted upon. And yet, the engineers kept calculating. At Johns Hopkins Applied Physics Laboratory, home to missions like New Horizons and Parker Solar Probe, a small team began sketching a minimum viable intercept architecture. The concept was brutal in its simplicity. A small spacecraft, stripped of redundancy, carrying only essential instruments. Launch on the largest available rocket. Use gravitational assists aggressively. Accept high risk. The mission would have perhaps a 30% chance of success. It would return limited data. It would cost upwards of $800 million. The proposal never left the internal review stage. On October 3rd, SpaceX announced a partnership with NASA to develop orbital refueling capabilities for Starship, enabling deep space missions in the late 2020s. The announcement was forward-looking, ambitious, and irrelevant to 3I Atlas. By the time Starship could chase interstellar objects, 3I Atlas would be light years away. Dr. Tanaka summarized the situation in a blog post. We built a civilization capable of observing the universe in exquisite detail. We did not build a civilization capable of responding to it quickly. The observation campaigns continued. Ground-based telescopes tracked the object nightly. Spectra accumulated. Thermal models refined. But we remained spectators, watching something extraordinary slip past while our spacecraft sat on launch pads, awaiting missions planned years in advance. This is the infrastructure gap that defines modern space exploration. We can see farther than ever before. We can measure with unprecedented precision. But we cannot reach what we observe. 3. Atlas didn't wait for our timelines to align. On October 5th, it crossed 3.5 astronomical units from the Sun. Surface temperatures exceeded -140 degrees Celsius. The glassy coating continued to channel heat inward, and subsurface thermal activity intensified. Something was building, and we could only watch. Chapter 5. October 1st, 2025. The dual-state surface. High-resolution photometry began on October 1st, when atmospheric conditions over Mauna Kea stabilized enough for adaptive optics to correct for turbulence. The Keck Observatory activated its near-infrared imager, achieving angular resolution fine enough to distinguish surface features on 3 Atlas, despite its distance and small size. The images revealed asymmetry. One hemisphere appeared darker, rougher, with irregular albedo variations suggesting extensive erosion. The other hemisphere was smooth, bright, with uniformly high reflectivity characteristic of fresh ice. The contrast was sharp, not gradual, not transitional, but abrupt. A line divided the two regions, running nearly pole to pole like a planetary terminator frozen in place. Dr. Nakamura assembled a team to model the thermal history required to produce such a division. Natural processes could, in theory, create hemispheric asymmetries. Tidal locking, where one side perpetually faces a heat source, produces temperature gradients. Impact events can pulverize one hemisphere while leaving the other intact. But 3I Atlas wasn't tidally locked. Its rotation period was consistent and stable, meaning both hemispheres received equal solar exposure over time. And impact events produce craters, ejecta blankets, chaotic, localized damage, not clean hemispheric boundaries. The erosion pattern on the dark hemisphere showed grooves, channels, and pits, features consistent with prolonged sublimation. Water ice had vaporized, leaving behind refractory residue. The texture resembled cometary surfaces observed by SA's Rosetta mission. Rough, porous, darkened by organic compounds. The bright hemisphere showed none of this. Its surface was pristine, as if freshly exposed or never heated. "This is a preservation boundary," Dr. Mora said, studying the images. One side experienced thermal processing. The other didn't. The team calculated the energy required to drive such differential heating. If the dark hemisphere had been exposed to sunlight while the bright hemisphere remained shaded, the temperature difference would need to persist for tens of thousands of years, time enough for sublimation to erode one side while preserving the other. But 3I Atlas had been in interstellar space for millions of years, far from any star. There was no heat source to drive hemispheric warming, unless the object had been oriented deliberately. Dr. Reinhardt modeled hypothetical trajectories where 3I Atlas passed close to a star, with its rotation axis aligned such that only one hemisphere faced the stellar flux. The geometry was possible, rare but possible. A slow rotation combined with a fast stellar flyby could expose one side to intense heating while the other remained cold. But the trajectory data showed no such encounter. On October 3rd, spectroscopic analysis from LLT provided chemical context. The dark hemisphere showed enriched carbon compounds, tholins, polycyclic aromatics, complex organics formed through radiation processing of methane and ammonia. These materials are common in the outer solar system, produced when ultraviolet light or cosmic rays break apart simple molecules and reassemble them into more complex chains. The bright hemisphere showed minimal organic content. The ice was chemically simple: water, methanol, carbon monoxide, unaltered, unprocessed. "This is a cryogenic archive," Dr. Mora said during a presentation to her ESO colleagues. One hemisphere was exposed to space weathering. The other was protected. Protected how? The most straightforward explanation involved rotation and geometry. If 3I Atlas had spent millennia oriented such that one pole perpetually faced away from cosmic radiation sources, perhaps while embedded in a dense molecular cloud, the shielded hemisphere could remain pristine while the exposed side accumulated damage. But cosmic rays are isotropic. They come from all directions. Shielding would require physical mass, not just geometry. The object would need to be buried in something. Dust debris, another body, that blocked radiation from reaching one hemisphere. No evidence of such burial existed. On October 6th, thermal infrared imaging from NASA's RDF revealed that the two hemispheres also had different temperatures. The dark hemisphere, despite its lower albedo, was cooler, emitting infrared radiation more efficiently, as if its surface structure facilitated heat dissipation. The bright hemisphere retained heat, radiating less despite receiving the same solar flux. This is counterintuitive, Dr. Nakamura noted. Dark surfaces usually absorb more heat. But here, the dark side is cooler. The explanation lay in surface texture. The eroded hemisphere had high porosity, voids, channels, and gaps that allowed heat to penetrate and radiate away efficiently. The smooth hemisphere was denser, less porous, trapping heat beneath a thin surface layer. This suggested different formation conditions or different modification processes, or both. Dr. Tanaka proposed a formation scenario where 3I Atlas began as a binary object, two small bodies orbiting each other, eventually colliding and merging. One body could have been thermally processed, the other cryogenically preserved. The collision would have fused them into a single, irregular shape, creating the observed hemispheric dichotomy. The hypothesis was plausible. Binary systems are common among asteroids and Kuiper belt objects. Collisions, while catastrophic, can produce stable merged bodies if the impact velocity is low enough. But spectroscopic data showed no compositional gradient, no mixing zone where two different materials blended at the collision interface. The transition between hemispheres was chemically sharp, as if the surfaces had been processed after merging, not before. On October 8th, Dr. Mora compiled the photometric, spectroscopic, and the thermal data into a comprehensive profile. She presented the findings during a virtual colloquium, attended by planetary scientists from 12 institutions. The conclusion was unambiguous. 3I Atlas exhibited dual-state surface characteristics that couldn't be easily explained by known cometary evolution. One hypothesis emerged as the least improbable: controlled thermal processing. If the object had been deliberately heated on one hemisphere, perhaps by positioning it near a star, or by using an internal heat source, the erosion pattern could be engineered. The bright hemisphere would remain cold, preserving pristine volatiles, while the dark hemisphere underwent sublimation, creating an insulating layer. This would be functional. A protective crust would shield the interior from future heating, while the smooth hemisphere could serve as a reflective surface for observational or navigational purposes. But invoking deliberate action required evidence beyond statistical improbability. Dr. Mora was careful in her phrasing. We observe features consistent with non-random thermal exposure. Whether this results from rare natural conditions or deliberate modification remains an open question. The community received the presentation with professional skepticism. Some argued that interstellar environments were poorly understood, and that rare natural processes could explain the observations. Others noted that the sheer number of anomalies, each individually improbable, suggested something beyond natural variation. No consensus formed. On October 10th, Hubble Space Telescope time was finally allocated for high-resolution imaging. The observation was scheduled for October 14th, contingent on spacecraft health and target visibility. Hubble could resolve features as small as 50 meters across, enough to detect surface structures, impact craters, or linear features that might indicate geological activity. The request emphasized surface morphology. Are the hemispheric boundaries truly sharp? Are there linear features suggesting fracture networks or flow patterns? Does the smooth hemisphere show any indication of artificial shaping? The observation was approved. Meanwhile, photometric monitoring continued. Dr. Tanaka tracked brightness variations as 3E Atlas rotated, watching for changes in the light curve that might indicate surface activity, jets, dust plumes, or structural collapse. The light curve remained stable, but the rotation period continued to slow. By October 11th, the period had lengthened to 11.9 hours, 0.5 hours slower than the initial measurement. Angular momentum was being lost. For a rigid body, this implied external torque. For a body with internal dynamics, it suggested mass redistribution, liquid shifting, gas venting, or material compressing under gravity. It's still changing, Dr. Tanaka said during a status update. Something inside is still active. On October 13th, ALMA completed a second millimeter wave observation, this time with longer integration time and higher sensitivity. The thermal emission maps showed that the subsurface hotspots had intensified. Temperatures 40 degrees above surface equilibrium were now concentrated in two symmetrical regions, aligned with the rotation axis. The pattern was no longer subtle. It was obvious. Dr. Mora cross-referenced the hotspot locations with the hemispheric boundary. The hotspots were not randomly placed. They lay precisely at the interface between the eroded and pristine regions, as if heat was being channeled along the boundary. "This is engineered," she said quietly during a team meeting. "I don't know how else to interpret it." Dr. Reinhardt offered a counterpoint. "Or it's a geological boundary where material properties change, creating a thermal pathway. Europa has similar features, cracks where subsurface oceans reach toward the surface, creating localized heating." Europa has Jupiter, Mora replied. "What does 3E Atlas have?" No one answered. The dual-state surface became the defining feature of 3E Atlas. It was reproducible, quantified, and inexplicable within conventional cometary models. Two hemispheres, one cold, one hot, divided by a line that shouldn't exist. Cold preserved it. Heat reshaped it. And the line between them was too precise to be accidental. Chapter 6, October 4th, 2025. Instruments that were never meant for this. The instruments observing 3I Atlas were designed for different questions. The Keck Observatory's spectrographs were optimized for distant galaxies and exoplanet atmospheres, objects that remain stationary against the stellar background. Fast-moving solar system bodies require different tracking algorithms, different exposure times, different calibration strategies. The engineering teams at Keck adapted. On October 4th, Dr. Mora's team requested a custom observation mode, continuous spectroscopy over an 8-hour window, tracking 3I Atlas as it moved against the background stars. The telescope's pointing system was designed for sidereal tracking, following the slow rotation of the sky. Tracking a fast-moving object required manual overrides, updated pointing coordinates every few minutes, and constant attention from telescope operators. The observation succeeded, but barely. The data showed gaps where tracking algorithms struggled, spectral lines that drifted across detector pixels, and signal-to-noise ratios lower than optimal. "We're pushing these instruments beyond their design limits," said Dr. Hiroshi Yamada, a Keck staff astronomer. "But it's working." This improvisation characterized the entire 3 Atlas campaign. Instruments built for one purpose were repurposed for another, often with incomplete calibration and untested workflows. The Very Large Array in New Mexico faced similar challenges. VLA was designed to observe radio emissions from distant quasars, pulsars, and star-forming regions, sources that remain fixed over observation periods. 3 Atlas moved fast enough that its position changed measurably during the 6-hour observation windows. The LA correlator, the computer system that combines signals from 27 individual dishes, had to be reconfigured to track a moving target. The software existed, but it was rarely used, poorly documented, and required manual setup. Dr. Reinhardt coordinated with VALA staff to implement the tracking mode. The observation succeeded, but the data pipeline downstream, designed to process stationary sources, struggled to handle the Doppler shifts and phase variations introduced by 3 Atlas's motion. "We're getting data," Reinhardt said during a team call. "But processing it is another story." Similar issues plagued ALMA in Chile. The array's 66 dishes operate as a single interferometer, combining signals to achieve angular resolution finer than any single telescope. But the combination requires precise timing, and moving targets introduce timing errors that degrade image quality. ALMA's observation of 3A Atlas required custom scripting, on-the-fly calibration adjustments, and post-processing techniques borrowed from solar system observations of Jupiter and Saturn. "We're making it work," said Dr. Sofia Delgado, an ALMA support scientist. But this is not how the system was designed to operate. NASA's Infrared Telescope facility faced different constraints. RTF is a workhorse facility, operating nearly every clear night, shared among dozens of programs. Each program receives limited time, and overruns are discouraged. Dr. Nakamura's thermal imaging campaign required consistent nightly coverage to track temperature changes as 3 Atlas approached the sun. But RTF's schedule couldn't accommodate nightly observations. Other programs had priority. The compromise involved short observations during gaps created by weather or technical issues. If clouds rolled in over Mauna Kea and canceled another program's time, 3 Atlas got a window. If an instrument failed and required maintenance, 3 Atlas filled the gap. The data arrived irregularly, with nights-long gaps, making temporal analysis difficult. "We're assembling a timeline from fragments," Nakamura said. "It's not ideal, but it's what we have." Hubble Space Telescope faced its own limitations. The observatory, launched in 1990, remains one of the most powerful optical telescopes ever built. But its instruments were never designed for fast-moving solar system objects. Hubble's pointing system uses gyroscopes and star trackers to maintain stability. Tracking a moving target requires predicting its position with arc-second precision, updated every few seconds. But for distant planets, this is manageable. For fast-moving interstellar objects, it's challenging. The Space Telescope, Science Institute's observation planning team, spent 3 days calculating the optimal observation window, accounting for 3 Atlas's motion, Earth's orbit, and Hubble's orbital constraints. The observation was scheduled for October 14th, during a brief period when all parameters aligned. "We get one shot," said Dr. Emily Torres, the program coordinator. "If we miss, the next opportunity isn't until November. And by then the geometry will be worse." Meanwhile, ground-based observatories face their own challenges. Atmospheric turbulence, the shimmering distortion that limits ground-based resolution, varies with altitude, humidity, and air currents. Adaptive optics systems compensate by measuring turbulence in real time and adjusting mirror shapes thousands of times per second. But adaptive optics requires a bright guide star near the target, a star that the system can use to measure atmospheric distortion. 3 Atlas was moving through sparse star fields, regions where bright guide stars were rare. Keck's operators searched for suitable stars, often finding none within the required proximity. When guide stars weren't available, the observations proceeded without adaptive optics, accepting lower resolution. "We're doing what we can," Dr. Yamada said, "but these are not optimal conditions." The European Southern Observatory's VLT faced similar issues. Its SPHERE instrument, designed to image exoplanets by blocking stellar light, could, in theory, resolve surface features on 3 Atlas. But SPHERE requires a bright central star to block, and 3A Atlas was faint, extended, and surrounded by empty sky. The instrument couldn't be used as designed. On October 7th, Dr. Mora proposed an alternative. Use LT's spectropolarimeter to measure polarized light reflected from 3EA Atlas's surface. Polarization reveals surface texture, grain size, and composition, information that complements direct imaging. The proposal was approved, but the instrument required recalibration. Spectropolarimetry modes are rarely used for solar system objects, and the calibration database lacked reference spectra for fast-moving targets. The team improvised, using standard stars to establish baseline polarization, then subtracting instrumental effects from the 3I Atlas observations. "We're making assumptions," Dr. Mora admitted. "But the alternative is no data at all." This improvisation carried risks. Instruments pushed beyond their design parameters produced data with uncertain reliability. Calibration assumptions introduced systematic errors. Processing pipelines, developed on the fly, lacked the validation that comes from years of testing. But the alternative was inaction. On October 9th, Dr. Tanaka summarized the situation in a blog post. "We're observing an interstellar object with tools built for galaxies, planets, and stars. It's like using a microscope to study mountains. It works, but not well." The data quality reflected this compromise. Spectral lines were noisy. Images were blurred. Thermal maps showed artifacts from incomplete calibration. Every measurement carried larger error bars than ideal. And yet, the patterns persisted. Despite the improvisation, despite the limitations, despite the noise, the dual-state surface remained. The subsurface heating persisted. The chemical contradictions held. "If we're seeing this through imperfect instruments," Dr. Morris said during a team meeting, "imagine what we're missing." The statement hung in the air. On October 11th, a preprint appeared on Arxiv, an academic server where researchers share preliminary results. The paper, authored by Mora, Reinhardt, Nakamura, and 12 co-authors, presented the complete observational dataset. The conclusions were carefully worded. 3 Atlas exhibits multiple anomalies that challenge conventional cometary formation and evolution models. While natural explanations remain possible, the cumulative improbability of observed features warrants continued high-priority observation and theoretical investigation. The paper avoided speculation. It presented data, error bars, and conservative interpretations. The community read between the lines. Within hours, the preprint had been downloaded over 5,000 times. Email threads exploded across professional networks. Some researchers praised the rigor. Others questioned the methodology. A few suggested that the anomalies were artifacts of instrumental limitations, not intrinsic properties of the object. Dr. Nakamura responded publicly, "We've considered instrumental artifacts extensively. The signal persists across independent instruments, observation modes, and analysis techniques. These are not errors. These are real." The debate intensified. On October 12th, NASA's Planetary Defense Coordination Office issued a brief statement acknowledging 3E Atlas's scientific interest and confirming that continued observation was proceeding. The statement included no assessment of the anomalies, no comment on their significance. Bureaucracy remained cautious. Meanwhile, the instruments continued their improvised campaign. Telescopes slewed across the sky, tracking a visitor from interstellar space with tools designed for stationary targets. Data accumulated, noisy, incomplete, but consistent. And 3I Atlas continued inward, approaching perihelion, moving toward the moment when solar heating would peak and the mysteries would either resolve or deepen. The instruments were inadequate, but they were all we had. Chapter 7, October 9, 2025. Chemistry that shouldn't coexist. Spectroscopy reveals the universe's fingerprints. Every element, every molecule, every chemical bond absorbs and emits light at specific wavelengths. By measuring which wavelengths are present or absent, astronomers can determine composition without ever touching the object. On October 9th, high-resolution spectroscopy from Veltes-UV's instrument revealed something impossible. The spectrum of 3E Atlas showed absorption lines for water ice at 3.1 micrometers, a signature of hydrogen-oxygen bonds in crystalline lattice structures formed at temperatures below -200 degrees Celsius. These bonds are stable, persistent, and diagnostic of deep freeze environments. The same spectrum showed emission lines from forsterite, a magnesium silicate mineral, at 11.3 micrometers. Forsterite forms at temperatures above 1200 degrees Celsius, in conditions where rock melts and recrystallizes. Water ice and forsterite should never coexist on a pristine surface. Water sublimates long before temperatures reach 1200 degrees. If forsterite formed, the water should be gone. If water persists, forsterite shouldn't exist, at least not in crystalline form detectable by spectroscopy. Dr. Lena Sorensen, the geochemist consulting on the project, stared at the spectrum for an hour before calling Dr. Mora. "This makes no sense," she said. "It's like finding ice and lava on the same plate." The team considered explanations. One possibility: spatial separation. If the water ice existed on one hemisphere and the forsterite on the other, they wouldn't need to coexist thermally. The measurements could be sampling different regions during different observation windows. But the spectroscopy was disk-averaged, capturing light from the entire visible surface, integrating contributions from both hemispheres. Both signals appeared simultaneously. They were co-located. Another possibility: temporal separation. Perhaps the object had been heated in the distant past, forming forsterite, which then became buried under fresh ice deposited later. The spectroscopy could be detecting surface ice and subsurface minerals. But spectral analysis showed both signatures at surface-level intensities. Buried forsterite would produce weaker signals, absorbed and scattered by overlying material. The signals were equally strong. Dr. Sorensen proposed a third option: incomplete thermal processing. If the object had been briefly exposed to intense heat, flash heating from a stellar flare, or rapid entry into a protoplanetary disk, forsterite could form in localized patches while most of the surface remained cold. But flash heating produces amorphous silicates, not crystalline forsterite. Crystallization requires sustained high temperatures, time for atoms to arrange into ordered lattices. The forsterite was crystalline. On October 11th, additional spectroscopy from Gemini North added more compounds to the inventory. The spectrum revealed enstatite, magnesium pyroxene, forms at 800 to 1000 degrees C. Diopside, calcium pyroxene, forms at 1300 degrees C. Olivine, iron magnesium silicate, forms at 1200, 1400 degrees C. All of these are high-temperature minerals, diagnostic of igneous processes, volcanic eruptions, impact melting, magma crystallization. And all of them appeared alongside water ice, stable below 160 degrees C, carbon monoxide ice, stable below 200 degrees C, methanol ice, stable below 180 degrees C. The temperature range spanned 1600 degrees. This is not a single thermal history, Dr. Sorensen said during an emergency team meeting. This is two histories overlaid. The team calculated formation probabilities. Natural environments where both extreme cold and extreme heat occur are rare, but not impossible. Protoplanetary disks, for instance, have regions near the star where temperatures exceed 1500 degrees, and outer regions where temperatures approach 30 Kelvin. Material can migrate between these zones through turbulence, accretion flows, or gravitational scattering. But migration takes time, thousands to millions of years. During that time, the high-temperature minerals would be exposed to cold, and the low-temperature ices would encounter heat. Chemical equilibration would occur. The minerals would accumulate ice mantles. The ices would sublimate when heated. 3. Atlas showed no equilibration. The minerals were bare, crystalline, unaltered. The ices were pristine, unprocessed. It's like they were assembled yesterday, Dr. Sorensen said. Dr. Nakamura modeled a scenario where 3E Atlas formed as an aggregate, a rubble pile of fragments from different thermal environments, loosely bound by gravity. Some fragments could be cold, icy, primordial. Others could be hot, rocky, igneous. But spectroscopy showed chemical mixing. The absorption lines weren't clustered spatially. They appeared uniformly across the disk-averaged signal. This implied intimate mixing at scales below observational resolution, not discrete fragments. It's heterogeneous at small scales, Nakamura concluded. Maybe micron-scale mixing, ice grains next to silicate grains. This raised a new question. How do you mix materials that form at vastly different temperatures without destroying one or the other? One answer: rapid quenching. If you heat rock to 1200 degrees, vaporize it, then rapidly cool the vapor in a cryogenic environment, the minerals could condense directly onto ice grains without melting them. This process occurs in industrial materials science, vapor deposition, where metal films are deposited onto substrates by cooling vaporized material. It requires controlled conditions, vacuum chambers, precise temperature gradients. It doesn't occur naturally in space. Or does it? Dr. Reinhardt proposed an astrophysical analog: protostellar outflows. Young stars eject high-velocity jets of gas and dust, heated to thousands of degrees near the star, then cooled as they travel outward into cold molecular clouds. Material in these jets could experience rapid thermal cycling, hot near the source, cold at the terminus. If 3I Atlas formed in such an environment, it might accumulate both high-temperature minerals and low-temperature ices. But the timeline didn't fit. Protostellar outflows last tens of thousands of years. 3I Atlas had been in interstellar space for millions of years. Any jet-formed aggregate would have had ample time to thermally equilibrate. We're missing a mechanism, Dr. Mora said. Something that can produce this chemistry quickly, then preserve it indefinitely. On October 13th, Dr. Sorensen compiled a detailed chemical inventory, cross-referencing every detected compound with formation conditions. She calculated the probability that all observed compounds could coexist naturally, given known astrophysical processes. The result: less than 1 in 20,000. This is not impossible. The universe is vast. Rare events occur constantly across billions of star systems. Probability doesn't prove impossibility. But it does suggest that something unusual happened. Dr. Mora added the chemistry anomaly to the growing list of improbabilities. Preservation despite interstellar exposure: 1 in 50. Vitrified surface without stellar heating: 1 in 200. Hemispheric thermal dichotomy: 1 in 300. Organized subsurface heating: 1 in 400. Coexisting high and low temperature chemistry: 1 in 20,000. Multiply them together: 1 in 4.8 billion. This assumes independence, that each anomaly is unrelated to the others. If the anomalies are correlated, if they share a common cause, the probability calculation changes. But what common cause produces cryogenic preservation and high-temperature chemistry simultaneously? Dr. Reinhardt offered a hypothesis during an October 15th team call. What if it's manufactured? The word landed heavily. If you wanted to build an interstellar probe, he continued carefully, you'd need materials that survive both deep cold and solar heating. You'd use refractory alloys for thermal shielding, compounds that withstand extreme temperatures. You'd preserve volatiles internally, water for propulsion or life support, methanol for chemical reactions. Then you'd create exactly the chemistry we're seeing. The team went silent. Dr. Mora responded cautiously. That's one hypothesis. But invoking technology requires evidence beyond improbability. We need signatures that can't be natural, not just unlikely, but impossible. What would that look like? Reinhardt asked. Isotopic anomalies, Dr. Sorensen suggested. Artificial isotopes, or ratios, that don't occur in nature. Organized structures, geometric patterns, repeated features. Electromagnetic emissions, signals, transmissions, anything that suggests communication. We haven't detected any of that, Mora said. Yet, Reinhardt added. On October 16th, the team drafted a supplementary preprint focusing exclusively on the chemical anomalies. The paper included detailed spectroscopy, thermochemical modeling, and probability estimates. The conclusions were cautious. The observed chemical assemblage is highly improbable under no natural formation scenarios. While we cannot exclude rare astrophysical processes, the cumulative evidence warrants consideration of alternative hypotheses, including the possibility of artificial modification. The phrasing was careful: consideration of alternative hypotheses, not evidence of technology. The paper acknowledged the low prior probability of artificial objects and emphasized the need for independent confirmation. The preprint was uploaded to Archive on October 17th. Within 6 hours, it had been downloaded 12,000 times. Media outlets picked up the story. Headlines ranged from cautious, interstellar object exhibits unusual chemistry, to sensational, scientists can't explain alien comet's composition. Dr. Mora declined most interview requests. When she did speak, she emphasized uncertainty. Representing data, not conclusions. The chemistry is unusual. That's all we can say definitively. But the public conversation had shifted. For the first time, serious scientists were publicly discussing the possibility, however remote, that three eyelets might not be entirely natural. The speculation was out, and there was no taking it back. Chapter 8. October 13th, 2025. Silence between signals. Radio astronomy listens to the universe's whispers. Celestial objects emit radio waves across a broad spectrum: thermal radiation from warm dust, synchrotron emission from magnetic fields, molecular lines from cold gas. These signals are faint, often buried in noise, requiring large antennas and long integration times to detect. On October 13th, the Very Large Array observed 3I Atlas across a frequency range from 1 to 10 GHz, wavelengths spanning 30 to 3 centimeters. The observation lasted 6 hours, cycling through different frequencies to build a complete radio spectrum. The data showed nothing unusual. No strong emission. No molecular line. No synchrotron radiation. The object was radio-quiet, emitting only faint thermal radiation, consistent with its temperature. But embedded in the noise were gaps. Dr. Reinhardt noticed them while reviewing the processed data. At specific frequencies, 1.42 GHz, 446 GHz, and 8.33 JOZ, the signal dropped below expected thermal levels. Not by much, perhaps 5 to 10%, but consistently across multiple observation cycles. These were absorption dips, moments when less radio energy reached the antennas than predicted. Absorption occurs when material between the source and observer absorbs radio waves. Interstellar gas clouds, for instance, absorb at the hydrogen line, 1.42 GHz, creating dark lanes in radio maps. Molecular clouds absorb at frequencies corresponding to rotational transitions of molecules, like carbon monoxide. But 3I, Atlas, was emitting its own thermal radiation. It wasn't behind an absorbing cloud. If absorption was occurring, it had to be happening on or near the object itself. Dr. Reinhardt cross-referenced the dip frequencies with known molecular transitions. 1.42 GHz is the hydrogen line, ubiquitous in space, but not expected around a comet unless significant outgassing was occurring. 446 GHz didn't match any common molecular line. 8.33 GHz was close to ammonia transitions, but offset by several megahertz. These don't align with natural chemistry, Reinhardt said during a review meeting. The team considered instrumental artifacts. Radio telescopes are sensitive to interference. Satellites, radar, even terrestrial electronics can produce spurious signals. The VIAS correlator includes filters to remove known interference sources, but subtle effects can slip through. Reinhardt checked the observation logs. The frequencies in question had been flagged by automated quality control, but not rejected. The dips appeared real, reproducible across multiple antenna baselines. They're coming from the object, he concluded. On October 15th, a follow-up observation was scheduled, this time with higher spectral resolution. The VLA's wideband correlator was configured to measure frequency variations at kilohertz precision, allowing detailed analysis of the dip profiles. The observation captured the same features. The absorption dips were narrow, only a few hundred kilohertz wide, and symmetrical, with sharp edges. Natural absorption lines are usually broader, shaped by thermal motion and pressure broadening. These were too clean. Dr. Reinhardt calculated the implied gas density required to produce the observed absorption. For hydrogen, at 142 GHz, the dip suggested a column density, amount of gas along the line of sight, of approximately 10 gigaton atoms per square centimeter. This is low by interstellar standards, but significant for a small object. If 3I, Atlas had a diffuse hydrogen envelope, it should be detectable in other ways: optical emission, ultraviolet absorption, mass loss rates. No such envelope had been detected. The gas isn't there, Dr. Tanaka said when consulted, or it's too faint for optical instruments. Another possibility emerged. The dips weren't caused by absorption. They were caused by emission, negative emission, if such a thing existed. Radio interference sometimes produces inverted signals, where terrestrial sources cancel astronomical signals through destructive interference. But this requires precise phase alignment, which is effectively impossible for natural sources. Dr. Reinhardt proposed an alternative interpretation during an October 17th team meeting. What if the dips aren't random? What if they're structured? He displayed the three frequencies on a screen: 1.42 GHz, 4.46 GHz, 8.33 GHz. These are harmonics, he said. Not exact, but close. Harmonics occur when frequencies are integer multiples of a fundamental frequency. Musical instruments produce harmonics. Vibrating strings resonate at multiples of their fundamental pitch. Radio transmitters produce harmonics as artifacts of signal generation. The team calculated the implied fundamental frequency if the three dips were harmonics, approximately 1.04 GHz. This frequency has no known astrophysical significance, Reinhardt noted, but it's within the range used for radar and telecommunications. The statement shifted the conversation. If the dips were artificial, engineered signals or interference patterns, They might represent communication, navigation beacons, or diagnostic emissions from malfunctioning equipment. Or they might be instrumental artifacts, subtle calibration errors, or statistical flukes. Dr. Mora urged caution. 3 data points do not establish a pattern. We need more observations, independent confirmation, and rigorous artifact testing before speculating about signals. Dr. Reinhardt agreed, but privately, he was troubled. On October 19th, he contacted colleagues at Arecibo Observatory, or what remained of it. The facility had collapsed in 2020, but its archived data remained accessible. He searched for historical observations of interstellar objects, comets, and asteroids at similar frequencies, looking for precedent. No similar absorption dips had been recorded. He expanded the search to include pulsar observations, where narrow absorption features are sometimes seen. Pulsars emit intense radio beams, and intervening gas clouds can absorb specific frequencies. But pulsar absorption lines are caused by known molecules. High O formaldehyde. The 3I Atlas dips matched none of these. On October 20th, Dr. Reinhardt submitted a formal request to the VA Allocation Committee for extended observation time, 20 hours spread across multiple days, covering frequencies from 0.5 to 15 GHz, with maximum spectral resolution. The request emphasized the anomalous nature of the dips and the need for comprehensive characterization. It did not speculate about artificial origins, but noted that ruling out instrumental artifacts required extensive testing. The committee approved 12 hours, contingent on schedule availability. Meanwhile, the initial data began circulating among radio astronomers. Some dismissed the dips as noise. Others suggested exotic natural explanations, maser emission, cyclotron radiation from charged particles, or quantum interference effects in cold plasma. A few noted quietly that the frequencies were suspiciously clean for natural processes. On October 22nd, Dr. Reinhardt received an email from Dr. Elara Singh, a SETI researcher at the University of California, Berkeley. Singh specialized in analyzing radio signals for signs of artificial origin, narrow bandwidth, frequency drift, modulation patterns. She had reviewed the 3I Atlas data. These dips are consistent with carrier wave suppression, she wrote. It's a technique used in radio engineering to reduce power consumption. You transmit the sidebands but suppress the carrier frequency. The result looks like absorption dips at harmonics of the suppressed carrier. I'm not saying this is artificial, she continued. But if it were, this is what it would look like. Dr. Reinhardt forwarded the email to Dr. Mora. Mora read it twice. We can't publish this, she said during a call. Not without independent confirmation and much more data. The moment we suggest SETI implications, the narrative becomes uncontrollable. But if it's real, Reinhardt began. If it's real, we need proof. Not hints, not suggestions. Proof. On October 24th, the VLA completed the extended observation run. The data showed the same 3 dips, now confirmed across multiple observation sessions, with consistent frequency positions and absorption depths. No additional dips appeared at other frequencies. No modulation patterns were detected. No signal drift, no time variation, no change in structure. Just 3 dips, narrow and symmetrical, appearing and disappearing as 3-OT rotated. Dr. Reinhardt analyzed the timing. The dips appeared when the smooth hemisphere faced Earth and disappeared when the eroded hemisphere rotated into view. The signal, if it was a signal, was directional. It's coming from the bright side, he told Mora. The preserved hemisphere. Mora reviewed the rotation phase analysis. The correlation was statistically significant, pp value below 0.01, meaning less than 1% probability of occurring by chance. This is no longer noise, she said quietly. This is structure. On October 26th, the team held an internal meeting to discuss next steps. The conversation was tense. Dr. Tanaka argued for immediate publication. If this is a detection, we have an obligation to report it. Dr. Nakamura urged restraint. If we're wrong, we'll be remembered as the team that cried alien. We need certainty. Dr. Mora proposed a middle path. We publish the detection as an unexplained phenomenon. We describe the data, acknowledge the anomalies, and invite independent follow-up. We don't speculate about origins. Dr. Reinhardt added, and we contact SETI at home, Breakthrough Listen, and other signal analysis groups. Let them run their algorithms. If there's a signal, they'll find it. The team agreed. On October 27th, a preprint was uploaded to Arxiev, narrow-band radio absorption features in 3 atlas, observations, and preliminary analysis. The paper described the dips, presented the data, and listed possible natural explanations, all of which were deemed unlikely but not impossible. The concluding paragraph was carefully worded. The observed features do not match known natural radio emission or absorption processes. While instrumental artifacts cannot be fully excluded, the consistency and structure of the dips suggest an intrinsic origin. Further observation and analysis are strongly recommended. No mention of SETI. No speculation about technology. Just data and uncertainty. The paper was downloaded 8,000 times in the first 4 hours, and the silence between signals became the loudest sound in the room. Chapter 9, October 18, 2025. The odds begin to stack. By mid-October, the anomalies were no longer isolated curiosities. They formed a pattern. Dr. Mora compiled a comprehensive assessment on October 18th, bringing together every measurement, every spectral line, every thermal map collected since September 14. The document ran to 47 pages, dense with graphs, tables, and error analyses. She titled it, 3 Atlas, Cumulative Anomaly Assessment. The introduction laid out the statistical framework. Each anomaly, considered individually, remained within the realm of natural possibility. Rare, but not impossible. Comets occasionally exhibit unusual chemistry. Surface dichotomies occur. Thermal anomalies happen. But probability compounds. When multiple low-probability events occur on a single object, the cumulative likelihood drops exponentially. This is basic statistics. If event A has a 1 in 100 chance, and event B has a 1 in 200 chance, and they're independent, the probability of both occurring together is 1 in 20,000. Even with aggressive adjustments, the cumulative probability remained below 1 in 100 billion. She added a cautionary note to the assessment. These estimates assume independence and rely on incompletely understood astrophysical processes. Unknown natural mechanisms may exist that explain the observations. However, the cumulative improbability suggests this object warrants exceptional scrutiny. On October 19th, she shared the assessment with the core team. Dr. Reinhardt responded first. This is compelling, but we need to address the obvious question. If this isn't natural, what is it? Dr. Nakamura was more cautious. Statistics don't prove origins. Rare events happen. We've observed 3 confirmed interstellar objects. That's not a representative sample. Maybe all interstellar objects look like this, and we just don't know it yet. Nearly. Then we need more data, Dr. Tanaka said. Compare 3 atlas to Oumuamua and Borisov. Are the anomalies shared or unique? The comparison began immediately. Oumuamua, the first confirmed interstellar object discovered in 2017, had exhibited its own anomalies. Its elongated shape, unusual brightness variations, and non-gravitational acceleration, likely from outgassing, though no coma was detected, sparked speculation about artificial origins. Subsequent analysis favored natural explanations, but uncertainty remained. Twy Borisov, discovered in 2019, appeared more conventional. A clearly active comet with a prominent coma and tail, compositionally similar to solar system comets. It had raised fewer questions. 3I Atlas fell between them. More anomalous than Borisov, less visually dramatic than Oumuamua. Dr. Tanaka compiled a comparison table, listing properties for all 3 objects. Surface activity. Oumuamua. None detected, but acceleration observed. Borisov, strong coma and tail. 3I Atlas, none detected, no acceleration measured yet. Composition. Oumuamua, unknown, too faint for spectroscopy. Borisov, standard cometary volatiles, water, C, N. 3I Atlas, contradictory, cryogenic, high-temp minerals. Shape. Oumuamua, highly elongated, 6:1 aspect ratio inferred. Borisov, likely spheroidal, typical comet nucleus. 3I Atlas, moderately elongated, 2:1 aspect ratio inferred. Thermal properties. Oumuamua, unusual, higher albedo than expected. Borisov, normal for active comet. 3I Atlas, dual state, one cold hemisphere, one warm. Radio properties. Oumuamua, not observed. Borisov, weak thermal emission, normal. 3I Atlas, structured absorption features. The pattern was clear. Each interstellar visitor was unique. There was no template, no standard profile. If nature produced this diversity, then perhaps extreme outliers like 3I Atlas were inevitable. But inevitable and probable are different concepts. On October 21st, Dr. Mora received an email from Dr. Abraham Loeb, a theoretical astrophysicist at Harvard and chair of the Galileo Project, an initiative dedicated to searching for evidence of extraterrestrial technological artifacts. Loeb had followed the 3I Atlas observations closely. He had previously argued that Oumuamua's properties were more consistent with artificial origin than natural formation, a position that drew both support and criticism. His email was brief. The statistics are compelling, but the real test is falsifiability. What observation would conclusively rule out artificial origin? Dr. Mora considered the question. Falsifying artificial origin required finding a natural mechanism that explained all the anomalies simultaneously, not just individually. Or it required detecting features definitively inconsistent with technology, chaotic internal structure, random chemical distribution, stochastic behavior. She replied, conclusive falsification may be impossible without direct sampling, but we can establish thresholds. If the radio features resolve into molecular emission, if the thermal asymmetry correlates with impact cratering, if the chemistry equilibrates as the object warms, those would favor natural origins. Ninwal, Nandi. And if none of that happens? Loeb asked in a follow-up. Mora didn't answer immediately. On October 23rd, the team held a video conference to discuss public communication strategy. The preprints were circulating widely, media inquiries were increasing, and speculation was intensifying across social media and science forums. Dr. Nakamura argued for silence. The more we say, the more we feed speculation. Let the data speak. Dr. Tanaka disagreed. Silence creates vacuum, and vacuum fills with noise. We should control the narrative, emphasize uncertainty, explain the process, make clear that we're investigating, not concluding. Dr. Mora proposed a middle approach, a carefully worded summary for the astronomy community, distributed through professional channels, with explicit guidance on how to discuss the findings publicly. The summary, released on October 24th, began, recent observations of interstellar object 3I Atlas have revealed multiple properties that do not fit conventional cometary models. While natural explanations remain under investigation, the cumulative statistical improbability warrants expanded observational campaigns and theoretical work. It continued, we emphasize that low probability is not evidence of artificial origin. The universe is vast, and rare natural processes undoubtedly occur. Our responsibility is to report what we observe, quantify uncertainties, and invite independent scrutiny. The summary concluded, extraordinary claims require extraordinary evidence. We do not yet have extraordinary evidence. We have extraordinary questions. The response was measured. Some colleagues praised the transparency. Others felt the team was still being too cautious, that the data justified stronger statements. A few accused them of sensationalism, arguing that discussing artificial origins at all, even to dismiss them, legitimized fringe speculation. Dr. Mora received over 200 emails in 3 days. Some were supportive. Some were hostile. Many simply asked, "What do you think it is?" She had no answer. On October 26th, Dr. Sorensen completed a detailed geochemical model attempting to explain the mineral coexistence naturally. She tested scenarios involving shock heating from hypervelocity impacts, radiative heating during passage through dense interstellar clouds, and exotic formation environments near supernova remnants or stellar collision debris. None worked. Hypervelocity impacts could produce high-temperature minerals, but they would also vaporize nearby ice. The minerals and ice couldn't survive adjacent to each other. Radiative heating in dense clouds could warm surfaces selectively, but the heating would be gradual, allowing thermal equilibration. The sharp chemical boundaries observed on 3A Atlas required rapid, localized thermal processing. Supernova environments could produce intense heat and cold in proximity, but they also produce specific isotopic signatures, enrichment in heavy elements, radioactive isotopes, unusual abundances. 3I Atlas showed none of these. "I can't make it work naturally," Sorensen admitted during an October 27th team meeting. "Every scenario I test either destroys the ice or fails to form the minerals." "What if the minerals formed first, then the ice was added later?" Dr. Nakamura suggested. "Then the ice would sublimate as soon as the object entered sunlight," Sorensen replied. "We're observing it now, inside Jupiter's orbit, and the ice is still there. It should be gone." The team fell silent. Dr. Reinhardt spoke carefully. "There is one scenario where the chemistry makes sense. If the object was engineered, if the minerals were applied as a coating, and the ice was stored internally with insulation, the coexistence becomes functional, not contradictory." "But that requires intent," Dr. Mora said. "Yes," Reinhardt agreed. "It does." On October 28th, a new preprint appeared on arXiv from an independent team at Caltech. The authors had reanalyzed all publicly available data on 3A Atlas using Bayesian statistical methods, a framework that weighs competing hypotheses based on how well they predict observations. They compared two models. Natural model, rare but known astrophysical processes. Artificial model, technologically modified object. The Bayesian analysis assigned probabilities to each model based on fit quality, parameter counts, simpler models are favored, and prior expectations. Natural objects are vastly more common than artificial ones. The result, even with a prior assumption that artificial objects are 1 billion times rarer than natural ones, the posterior probability of the artificial model was 12%. This didn't mean 3A Atlas had a 12% chance of being artificial. Bayesian analysis reflects model fit, not truth. But it meant the artificial hypothesis was no longer statistically negligible. The Caltech paper concluded, "We do not claim 3A Atlas is artificial. We claim that artificial origin can no longer be dismissed on statistical grounds alone." The paper was downloaded 20,000 times in 12 hours. On October 29th, NASA issued a statement. NASA is aware of ongoing observations of interstellar object, 3I Atlas, and the associated scientific discussion. While the object exhibits unusual properties, current data do not support definitive conclusions about its origin. NASA encourages continued observation and analysis through peer-reviewed channels. The statement was careful, neutral, and revealing in its restraint. NASA neither endorsed nor dismissed the artificial hypothesis. They simply acknowledged uncertainty, which was itself significant. By the end of October, the odds had stacked. 14 anomalies. Quadrillion to 1. Cumulative improbability. Bayesian models that couldn't dismiss artificial origins. And a chemistry that made sense only if someone had assembled it deliberately. This wasn't proof, but it was no longer dismissible. The universe had presented a question we couldn't answer with the tools we had, and the clock was running out. 3I Atlas would reach perihelion on November 8th. After that, solar glare would make observation impossible for months. Whatever we were going to learn We needed to learn it in the next 10 days. The odds had stacked, and the questions kept multiplying. Chapter 10. October 22, 2025. A telescope turns away. On October 22, the James Webb Space Telescope was scheduled to observe 3 Atlas. JWST, the most powerful infrared observatory ever built, had the sensitivity to resolve surface features, map chemical distributions, and detect faint thermal emissions, invisible to ground-based instruments. A single 8-hour observation could answer questions that had plagued the team for weeks. The observation had been proposed in mid-September, shortly after 3 Atlas was confirmed as Interstellar. The science case was strong: unprecedented opportunity to study an interstellar visitor with humanity's most capable telescope. The Space Telescope Science Institute's Time Allocation Committee reviewed the proposal in late September. They acknowledged the scientific value, but noted competing priorities. JWST's schedule was fully booked through December, allocated to deep-field galaxy surveys, exoplanet atmospheric characterization, and a multi-instrument campaign studying early universe star formation. The committee placed 3 Atlas in the director's discretionary time category, reserved for urgent, unpredictable targets that justified schedule interruptions. But urgency is subjective. On October 15th, Dr. Mora received an email from the STCI director's office. The email explained that JWST observations required extensive planning: instrument configurations, pointing coordinates, exposure sequences, all uploaded to the spacecraft days in advance. Emergency observations were possible, but they disrupted carefully orchestrated campaigns months in the making. The email concluded, "Given current data on 3 Atlas, we do not assess the target as meeting emergency criteria. We recommend submission to the next regular proposal cycle, with observations scheduled for early 2026. By early 2026, 3 Atlas would be beyond Neptune, receding into interstellar space, too faint for detailed study. The opportunity would be gone." Dr. Mora drafted a response emphasizing the time-sensitive nature: perihelion approach, closing observation windows, anomalies requiring high-resolution follow-up. She attached the cumulative anomaly assessment, the spectroscopic contradictions, the radio absorption features. The reply came 3 days later: "We recognize the scientific interest. However, JWST cannot accommodate all worthy targets. We encourage maximizing ground-based observations during the current window." The decision was final. On October 22nd, at the scheduled observation time, JWST was pointed toward a galaxy cluster 4 billion light-years away, mapping gravitational lensing effects around dark matter halos. The science was valuable. The choice was defensible. And 3 Atlas drifted past, unobserved by humanity's most powerful eye. This wasn't the first time observation priorities had shifted away from 3 Atlas. On October 10th, the European Space Agency's Gaia spacecraft, a mission dedicated to mapping stellar positions with micro-arcsecond precision, had been scheduled to image 3 Atlas during a routine sky scan. Gaia's astrometric precision could have refined the object's trajectory, constraining its origin point in interstellar space to within light-years. But Gaia's observation schedule is automated, optimized for stellar mapping, not solar system objects. Inserting a special target requires manual commanding and interrupts the systematic survey pattern. ESA's Gaia operations team reviewed the request. They noted that interrupting the survey for a single object, no matter how interesting, would create gaps in stellar coverage that couldn't be recovered. The mission's primary science objective was the star map, not transient targets. The request was declined. On October 18th, NASA's Chandra X-ray Observatory was scheduled to observe a supernova remnant in the Large Magellanic Cloud. The observation had been planned for 18 months, coordinated with radio telescopes and optical observatories to study shockwave propagation in real time. Dr. Reinhardt submitted a request to divert Chandra toward 3 Atlas for 4 hours, enough time to detect X-ray emission from solar wind interactions, high-energy particle collisions, or other processes that might explain the thermal anomalies. Chandra's scheduling committee weighed the request. X-ray observations of comets are rare. Most don't emit detectable X-rays. The likelihood of a positive detection was uncertain. Meanwhile, the supernova observation was guaranteed to return valuable data, coordinated with multiple facilities, and represented a rare alignment of multi-wavelength coverage. Chandra observed the supernova. On October 25th, the Hubble Space Telescope finally completed its scheduled observation of 3E Atlas, the high-resolution imaging that had been planned since early October. The data showed surface details at 50-meter resolution, irregular topography on the dark hemisphere, smooth plains on the bright hemisphere, and what appeared to be linear features running parallel to the hemispheric boundary. Linear features. Dr. Mora examined the images for hours. The features were subtle, variations in albedo just barely above the detection threshold. They could be fracture lines, grooves carved by sublimation, or compression ridges from tidal stress. They could also be seams. She requested follow-up imaging with different filters, optimized for detecting compositional variations along the linear features. The request was submitted on October 26th. Hubble's schedule was already overbooked through November. The earliest available time slot was December 3rd, well after perihelion, when 3 and Atlas would be fainter and farther from Earth. The follow-up observation was tentatively approved, contingent on spacecraft health and scheduling conflicts. It wasn't guaranteed. Meanwhile, ground-based observatories faced their own constraints. On October 28th, a tropical storm moved over Hawaii, bringing cloud cover to Mauna Kea. The forecast predicted 5 days of poor weather, no observations from Keck, Gemini North, or the NASA Infrared Telescope facility. 5 days represented 10% of the remaining observation window before perihelion. In Chile, the Atacama Large Millimeter Array faced similar challenges. Alma's high-altitude site offered dry skies most of the year, but late October brought seasonal weather variability. Observations scheduled for October 29th and 30th were canceled due to moisture levels that compromised receiver sensitivity. The data gaps accumulated. On October 30th, Dr. Tanaka compiled an observation timeline, marking every scheduled session, weather cancellation, and telescope conflict. The timeline showed a pattern. 3 Atlas received observation time only during gaps, when weather disrupted other programs, when instruments needed recalibration, when scheduled targets weren't visible. The object had become an opportunistic target, observed when convenient rather than when scientifically optimal. "We're collecting scraps," Tanaka said during a team meeting. "Not a systematic dataset." Dr. Nakamura pushed back. "We're collecting what the system allows. Unless someone declares this an emergency and overrides priorities, this is what we get." "Who has that authority?" Dr. Tanaka asked. "For NASA facilities, the agency director. For ESA, the science director. For private observatories, the boards of directors. And none of them have declared an emergency. Because we haven't proven it is one." The circular logic was maddening. To prove 3, Atlas warranted emergency status. They needed comprehensive data. To get comprehensive data, they needed emergency status. And to get emergency status, they needed proof the anomalies couldn't wait. But the anomalies were time-sensitive by definition. Perihelion approached whether anyone declared emergency or not. On November 1st, Dr. Mora drafted a formal request to NASA's Science Mission Directorate, appealing for emergency observation priority across all available NASA facilities. The letter outlined the cumulative anomalies, the statistical improbability, and the irreversible loss of scientific opportunity if observations ceased. The letter included a cautiously worded paragraph. "While we do not claim artificial origin, the possibility cannot be excluded based on current data. If 3I Atlas represents technological material, however unlikely, the scientific and societal implications justify extraordinary observational effort." The letter was co-signed by Reinhardt, Nakamura, Tanaka, Sorensen, and 23 other scientists who had contributed to the observations. It was sent on November 2nd. NASA's response arrived on November 4th. "We acknowledge the scientific significance of 3I Atlas and commend the observational campaign to date. NASA facilities will continue to provide observation time as scheduling permits. However, based on current data, We do not assess the situation as meeting emergency criteria, requiring override of planned science operations. The response included a procedural note. Extraordinary claims require extraordinary evidence. At present, the data suggest an unusual natural object, not definitive anomalies requiring exceptional measures. The message was clear. Keep observing when you can, but don't expect priority. Dr. Mora read the response twice, then closed her laptop. On November 5th, the weather over Mauna Kea cleared. Keck Observatory resumed operations. Dr. Mora's team had 4 hours of scheduled time, enough for one high-resolution spectroscopic observation. The observation captured 3E Atlas as it rotated, cycling through different viewing geometries. The data showed the same contradictory chemistry, ice and high-temperature minerals coexisting impossibly. But the spectral lines were beginning to change. Water-ice absorption was weakening. The object was warming, sublimating, losing volatiles. Within days, the pristine surface would be gone, replaced by a desiccated crust that revealed nothing about its original state. The object was changing, and the window was closing. On November 6th, Dr. Reinhardt ran trajectory projections. After perihelion on November 8th, 3 Atlas would begin its outward journey, accelerating under the sun's gravity assist. By late November, it would be fainter than magnitude 22, beyond the reach of most ground-based instruments. By December, only GUSD and Hubble could track it, and both had declined extended observations. By February 2026, it would be undetectable. Humanity's first comprehensive look at an interstellar object with potential artificial characteristics would end not with answers, but with bureaucratic inertia and scheduling conflicts. The telescopes turned away, one by one, returning to planned observations of galaxies, exoplanets, and distant stars. And 3E Atlas continued inward, carrying its mysteries toward the sun. Chapter 11, October 27, 2025. Cold origin, hot intent. The trajectory told a story written in gravity. On October 27th, Dr. Reinhardt completed a comprehensive orbital reconstruction, tracing 3 Atlas backward through time, with unprecedented precision. The analysis integrated positional measurements from 14 observatories across 6 weeks, correcting for gravitational perturbations from planets, solar radiation pressure, and relativistic effect. The result was a path through space and time, extending millions of years into the past. 3I Atlas had not come from any nearby star system. The closest stellar encounter, the red dwarf in Lynx, 2.1 million years ago, had been too distant to perturb the trajectory significantly. Before that, the object had traveled through interstellar space for at least 3 million years, possibly much longer. But trajectories carry more than history. They carry intent. Or at least, they carry optimization. Dr. Reinhardt noticed something unusual while analyzing the trajectory's geometry. Interstellar objects entering the solar system from random directions should have randomly distributed trajectories, some passing through the inner system, some staying the outer system, some approaching the sun closely, others remaining distant. 3 Atlas's trajectory was not random. The object had approached from high ecliptic latitude, 34 degrees above the plane of planetary orbits, allowing it to avoid gravitational scattering by Jupiter and Saturn during infall. Its perihelion distance was calculated at 0.97 astronomical units, just inside Earth's orbit, close enough to the sun for significant heating, but not so close as to risk catastrophic thermal destruction. The geometry was efficient. This trajectory maximizes solar exposure while minimizing gravitational disruption, Reinhardt said during a November 1st team briefing. It's not proof of design, but it's the kind of path you'd choose if you wanted controlled solar heating. Dr. Nakamura challenged the interpretation. Or its selection bias. We detect interstellar objects that pass through the inner system because they're brighter and closer. Objects that stay in the outer system remain undetected. The trajectory seems optimal because those are the only ones we see. True, Reinhardt conceded. But even among detected interstellar objects, this one is unusual. Oumuamua passed much closer to the sun, 0.25 AU, and experienced much stronger heating. Borisov stayed farther out, around 2:00 at perihelion. 3 Atlas is threading the needle. No Hyundai. Dr. Mora examined the trajectory plots. The path curved gracefully through the solar system, entering from above, sweeping inward past Mars, approaching the Sun at a precisely calculated distance, then departing on a mirror trajectory back toward interstellar space. What would happen if you wanted to thermally process an object using solar heating? She asked Reinhardt. What trajectory would you choose? Reinhardt thought for a moment. You'd approach slowly, to allow time for heat to penetrate. You'd maintain a perihelion distance that provides strong but not catastrophic heating. Maybe 1:0, where solar flux is manageable. You'd avoid close planetary encounters that could alter your path, and you'd approach from high inclination to minimize perturbations. You'd choose this trajectory, Mora said quietly, or something very close to it. The team fell silent. On November 2nd, Dr. Nakamura ran simulations testing whether 3 Atlas's trajectory could result from a gravitational slingshot around a distant star, a scenario where the object's path was shaped by stellar gravity rather than deliberate guidance. He modeled hundreds of stellar encounters, varying approach distances, velocities, and stellar masses. Some encounters produced trajectories similar to 3 Atlas's path through the solar system, but they required highly specific initial conditions, stellar flybys at precisely calculated distances and speeds. The probability of a random interstellar trajectory naturally aligning with optimal solar thermal processing geometry was approximately 1 in 800. Not impossible, but another entry on the growing list of improbabilities. Meanwhile, thermal modeling continued. Dr. Nakamura's team projected surface temperatures during perihelion, accounting for the object's rotation, albedo variations, and the protective vitrified coating. The predictions were striking. At perihelion, the bright hemisphere would reach approximately 80 degrees Celsius, cold by terrestrial standards, but warm enough to drive sublimation in exposed water ice. The dark hemisphere, with its eroded crust and higher thermal conductivity, would reach 60 degrees Celsius. But subsurface temperatures would be much higher. The ALMA thermal maps showed subsurface heating concentrated at the hemispheric boundary, the interface between preserved ice and thermally processed crust. At perihelion, those regions would reach 0 degrees Celsius. Water's melting point. Liquid water, deep inside an interstellar object, heated by controlled solar exposure. If this is natural, Dr. Nakamura said, reviewing the thermal projections, it's the most thermally sophisticated natural process I've ever seen. Dr. Zoranzan completed a parallel analysis focused on the vitrified coating's thermal properties. Vitrified silicates, glassy minerals formed by rapid cooling of molten rock, have unusual thermal characteristics. They're poor conductors, trapping heat beneath the surface. They're also optically selective, absorbing visible light efficiently while radiating infrared less effectively. These properties make vitrified coatings ideal for thermal management, spacecraft heat shields, re-entry vehicles, solar concentrators. This coating is functional, Sorensen concluded. It protects the interior while channeling heat to specific regions. If you wanted to melt subsurface ice using solar heating, you'd design exactly this kind of surface. Dr. Mora asked the obvious question. Can this coating form naturally? Sorensen hesitated. Vitrification requires melting, which requires intense heat. The heat could come from impacts, high-velocity collisions that vaporize rock and flash freeze it into glass. But impacts are random, chaotic. They produce localized melt patches, not uniform coatings. And 3I Atlas has a uniform coating? We can't measure uniformity directly. Our resolution isn't good enough. But the spectroscopy shows vitrified silicates across multiple regions, including both hemispheres. That suggests widespread, not localized, thermal processing. Which requires widespread heating. Yes. From what source? Sorensen had no answer. On November 4th, a new hypothesis emerged from an unexpected direction. Dr. Elara Singh, The SETI researcher who had analyzed the radio absorption features contacted Dr. Mora with a speculative proposal. What if 3I Atlas is a sample return mission? Singh suggested during a video call. Not inhabited, not actively controlled, just an automated system designed to collect interstellar material and process it using solar heating. Dr. Mora considered the idea. You mean it scooped up ice and dust during its interstellar journey, then used the sun to analyze or refine the material? Exactly. Solar heating is free energy. If you're traveling between star systems, why carry fuel for onboard processing when you can use stellar radiation? You design the trajectory to optimize solar exposure, coat the exterior for thermal control, and concentrate heat where you need it. But why would anything, go to that effort? Singh shrugged. Scientific curiosity? Resource extraction? Proof of concept testing? We launch automated probes all the time. Voyager, New Horizons, the upcoming interstellar missions. They're not crude, not intelligent, just instruments following pre-programmed instructions. You're describing a von Neumann probe, Dr. Mora said. Self-replicating, automated, spreading through the galaxy. Not necessarily self-replicating, just automated. A probe sent out millions of years ago by a civilization that might not even exist anymore. The hypothesis was speculative, unstable, and disturbingly plausible. Dr. Mora shared Singh's proposal with the team on November 5th. The response was mixed. Dr. Reinhardt found it compelling. It explains the trajectory, the thermal management, the chemistry. You collect ice in deep space, heat it with solar flux, extract volatiles, or analyze composition. The object becomes a traveling laboratory. Dr. Nakamura was skeptical. It's a hypothesis that fits the data, but so do a dozen natural explanations we haven't thought of yet. We're pattern-matching observations to our own technology. That's anthropocentric reason. Dr. Tanaka offered a middle view. We can't assume it's artificial, but we also can't ignore that the artificial hypothesis is internally consistent. Natural explanations keep requiring new, rare processes to explain each anomaly. The artificial hypothesis explains them all with a single assumption. Which is a simpler explanation? Dr. Mora asked. That depends, Tanaka replied, on your prior probability for extraterrestrial technology. The question had no objective answer. Bayesian analysis depends on priors, initial assumptions about how likely something is before considering evidence. If you assume technological artifacts are vanishingly rare, natural explanations always win. If you allow for the possibility that advanced civilizations send automated probes, artificial explanations become competitive. The choice of prior was philosophical, not scientific. On November 6th, the team drafted a supplementary paper titled Trajectory Analysis and Thermal Optimization in 3I Atlas. The paper presented the orbital reconstruction, thermal modeling, and efficiency metrics without speculating about origins. The abstract concluded, the observed trajectory and thermal properties are consistent with optimized solar thermal processing. Whether this optimization results from selection bias, rare astrophysical processes, or deliberate design remains an open question. The paper was submitted to Nature Astronomy on November 7th, one day before perihelion. By the time peer review completed, 3I Atlas would be departing, its surface transformed by solar heating, its mysteries potentially deepened or resolved. Cold had preserved it for millions of years, shielding pristine volatiles in the darkness between stars. Heat was reshaping it now, channeling energy through vitrified coatings towards subsurface regions designed, or evolved, to absorb it. And the trajectory had brought it here, to this star, at this distance, with this geometry. By accident, or intent. We still didn't know. Chapter 12, November 2nd, 25, When Data Outpaces Policy. On November 2nd, Dr. Mora received a phone call from NASA's Planetary Science Division. The call was brief, formal, and carefully worded. A program manager explained that NASA was monitoring the situation regarding 3I Atlas, and appreciated the scientific diligence of the observational campaign. The agency requested advance notice before any public statements that might raise societal concerns or require an aided response. The message was clear. If you're going to suggest this might be artificial, tell us first. Dr. Mora understood the reasoning. If 3I Atlas were even plausibly technological, the implications extended beyond astronomy. International treaties governed responses to potential extraterrestrial contact. Government agencies, NASA, the Department of Defense, intelligence communities, had protocols for evaluating and communicating such discoveries. Those protocols assumed orderly, controlled information flow. They did not assume data circulating in real time on preprint servers, analyzed by independent researchers worldwide, discussed openly in academic forums. We're not making claims about artificial origin, Mora told the program manager. We're reporting observations and acknowledging statistical anomalies. We understand, the manager replied. But public interpretation may not distinguish between reporting anomalies and suggesting technology. We ask that you coordinate messaging through appropriate channels. Appropriate channels? The NASA Office of Communications, the International Astronomical Union, and relevant governmental bodies. Dr. Mora noted the plural, governmental bodies. Not just NASA. Multiple agencies, across multiple countries. We're scientists, not policymakers, she said carefully. Our responsibility is accurate data reporting. Of course, we simply request coordination. In the interest of clarity and public understanding. The call ended politely, but the subtext lingered. NASA was concerned, not about the science, but about the narrative. On November 3rd, Dr. Mora discussed the call with the team. Dr. Reinhardt was blunt. They're asking us to self-censor. They're asking for coordination, Dr. Nakamura corrected. That's reasonable. If this were a pandemic virus or a nuclear incident, we'd coordinate with public health or safety authorities. Why should this be different? Because it's not a threat, Reinhardt replied. It's a scientific question. Unless it's not just scientific, Dr. Tanaka said quietly. If there's even a chance this is technology, it becomes political, strategic, existential. Governments will want control over messaging. Dr. Mora summarized the dilemma. We have data that's already public, circulating in preprints and conference presentations. We can't unpublish it. But we also can't ignore requests for coordination from the agencies that fund most of our work. So what do we do? Dr. Nakamura asked. We report the data accurately. We emphasize uncertainty. And we give NASA advance notice before major announcements. That's transparency, not censorship. The team agreed, but unease remained. Meanwhile, the data continued to escape controlled channels. On November 4th, a Reddit post appeared in the r/astronomy subreddit. Is 3 Atlas artificial? The evidence is stacking up. The post linked to all the published preprints, included summary charts of the anomalies, and presented the cumulative probability calculations. Within 12 hours, the post had 8,000 upvotes and over 1,200 comments. The discussion ranged from rigorous scientific critique to wild speculation. Some commenters dismissed the artificial hypothesis as sensationalism. Others argued the evidence was compelling. A few suggested government cover-ups or conspiracy theories. The post was cross-posted to r/space, r/physics, and r/UFOs. Each community interpreted the data through different lenses: skeptical, analytical, enthusiastic. Dr. Mora watched the discussion with a mix of fascination and frustration. Some comments demonstrated genuine understanding of the science. Others misrepresented the data, claiming definitive conclusions where none existed. On November 5th, a science journalist from The Atlantic emailed Dr. Mora requesting an interview. The subject line: 3 Atlas. Are we observing first contact? Dr. Mora declined. The data do not support first contact framing. We're studying an unusual object. That's all we can say definitively. The journalist replied, with respect, Dr. Mora, You've published papers acknowledging the possibility of artificial origin. The public deserves to understand what that means. The public deserves accurate reporting, Mora wrote back, not premature speculation. The exchange illustrated the gap between scientific communication and public understanding. Scientists speak in probabilities, uncertainties, conditional statements. Media speaks in narratives, implications, human interest. The gap was unbridgeable. On November 6th, a preprint appeared on ArcSafe from an independent team at MIT. The paper, titled Biosignature Potential of Interstellar Objects, Implications for Panspermia and Detection Strategies, argued that if 3 Atlas contains subsurface liquid water, as thermal modeling suggested, it could theoretically harbor microbial life. The paper was speculative, based on assumptions about internal structure and chemistry. But it raised a new question. Should 3 Atlas be treated as a potential biohazard? Planetary protection protocols exist to prevent biological contamination between Earth and other solar system bodies. The protocols are strict for Mars, Europa, and Enceladus, worlds where indigenous life might exist. But interstellar objects had never been considered in planetary protection frameworks. If 3 Atlas contained life, however unlikely, and fragments entered Earth's atmosphere during future orbits or collision events, could that life contaminate terrestrial ecosystems? The MIT paper concluded, while the probability of viable biosignatures is low, the consequences of contamination warrant precautionary observation and trajectory monitoring. NASA's Planetary Protection Office issued a statement on November 7th. 3 Atlas poses no biosecurity risk to Earth. The object's hyperbolic trajectory ensures it will not collide with Earth, and atmospheric entry of any ejected material would sterilize biological content through thermal heating. The statement was reassuring and technically accurate. It did not address the underlying anxiety. We were observing something we didn't understand, and uncertainty breeds concern. On November 8th, Perihelion Day, Dr. Mora received another call, this time from the International Astronomical Union's Executive Committee. The EIU coordinates global astronomical research and manages nomenclature, classification, and communication protocols for significant discoveries. The committee requested a briefing on 3 Atlas, specifically addressing the artificial origin hypothesis. Dr. Mora presented the data: cumulative anomalies, statistical improbabilities, chemical contradictions, trajectory efficiency, thermal management. She emphasized that each anomaly had potential natural explanations, but the collective pattern was difficult to reconcile naturally. "What's your personal assessment?" an IIU committee member asked. Dr. Mora paused. "I think we're observing something outside our current understanding of cometary science. Whether that means rare natural processes or something else, I cannot say with confidence. Do you believe it's artificial? Belief is not relevant. Evidence is. And the evidence is ambiguous." The committee thanked her and ended the call. On November 9th, the day after perihelion, an internal IIU memo leaked to the press. The memo summarized the briefing and included a statement. The IIU acknowledges ongoing investigation of 3 Atlas and recognizes that current data do not exclude technological origin. However, extraordinary claims require extraordinary evidence, which has not yet been presented. The leak was accidental, but the damage was done. Major news outlets picked up the story. Headlines proliferated. The New York Times: astronomers can't rule out artificial origin for interstellar visitor. BBC: is 3 Atlas a probe? Scientists urge caution. CNN: mysterious object from beyond solar system baffles scientists. Dr. Mora's inbox flooded with interview requests. She declined most, agreeing only to brief statements emphasizing uncertainty. One statement, issued jointly with the observational team on November 10th, read, 3 Atlas exhibits properties that challenge conventional models. We are committed to rigorous analysis and transparent reporting. Speculation about origins, natural or artificial, should be based on evidence, not imagination. We encourage patience as observations continue. The statement was measured, professional, and immediately ignored by the media ecosystem, hungry for definitive narratives. On November 11th, Dr. Reinhardt received a call from a colleague at SETI Institute. The colleague requested access to the raw radio data, the Valley observations showing narrowband absorption features. "We want to run it through our signal processing algorithms," the colleague explained. "The ones we use for candidate technosignature detection. If there's structure in the signal we missed, we'll find it." Dr. Reinhardt agreed. The data was already public, hosted on observatory archives. SETI teams had every right to analyze it. The results arrived on November 13th. SETI's algorithms detected no modulation, no time variable patterns, no characteristics consistent with intentional transmission. "The absorption features are real," the SETI colleague reported. "But they're not communication signals. If they're artificial, they're unintentional, leaked emissions or diagnostic noise, not messages." The finding was both reassuring and disappointing. No alien transmission, but also no natural explanation. On November 15th, as 3AS receded past Earth's orbit, Dr. Mora reflected on the past 2 months. The data had outpaced policy. Observations had generated questions faster than institutions could process them. And the public conversation had spiraled beyond scientific control. "We live in an era where data is immediate, global, and uncontrollable," she told Dr. Nakamura during a late-night call. "We can't gatekeep discovery anymore. The moment we publish, the world interprets." "Is that bad?" Nakamura asked. "It's reality," Mora replied. "And we need to adapt." Data had outpaced policy, and there was no going back. Chapter 13, November 8, 2025. What survives the crossing? Perihelion occurred at 14:23 Universal Time on November 8. At that moment, 3I Atlas reached its closest approach to the Sun. 0.972 astronomical units, approximately 145 million kilometers, just inside Earth's orbit. Solar flux at this distance measured 1060 watts per square meter, enough energy to sublimate bare water ice rapidly, to heat rock surfaces above 100 degrees Celsius, to drive explosive outgassing in any ordinary comet. 3I Atlas was not ordinary. Ground-based observatories across 3 continents tracked the object as it swept through perihelion. Thermal infrared imaging from NASA's RDF captured surface temperatures in real time. Spectroscopy from Keck and Velti monitored chemical changes. Radio observations from the Valley listened for outgassing signatures or electromagnetic emissions. Dr. Nakamura watched the thermal data arrive, updating every 20 minutes as 3 Atlas rotated. Surface temperatures on the bright hemisphere reached 85 degrees Celsius, cold by terrestrial standards, but the warmest the object had been in millions of years. The dark hemisphere reached 55 degrees Celsius, slightly warmer due to its lower albedo and higher thermal conductivity. But the subsurface was much hotter. ALMA's millimeter wave observations, conducted during the perihelion window, detected thermal emission consistent with temperatures approaching 5 degrees Celsius at shallow depths, less than a meter beneath the surface. In the concentrated heating zones near the hemispheric boundary, temperatures reached 10 degrees Celsius, above freezing. Liquid water. "It's melting," Dr. Nakamura said during the live observation session, watching the thermal maps update. "Subsurface ice is transitioning to liquid." Dr. Mora, monitoring from her office in Germany, asked the critical question, "Is the structure stable? Are we seeing outgassing, eruptions, disintegration?" "No," Nakamura replied. "Surface temperatures are rising, but there's no evidence of catastrophic disruption. The object is holding together." This was the moment of truth. Comets approaching perihelion either survive or disintegrate. The boundary depends on structural integrity, composition, and thermal management. Weak comets fragment under thermal stress, tidal forces, or pressure from sublimating gas. Strong comets develop protective crusts and endure. 3 Atlas was enduring. Spectroscopic monitoring showed subtle changes. Water ice absorption lines weakened slightly, evidence of surface sublimation. But the decline was gradual, controlled, not the explosive vaporization expected from exposed ice. Carbon monoxide and methanol lines remain nearly constant, suggesting these more volatile compounds were either depleted from the surface or buried beneath protective layers. The high-temperature mineral signatures, forsterite and statite, olivine, remained unchanged. The vitrified coating was intact, functioning as predicted, absorbing solar energy, channeling heat inward, protecting volatiles from direct exposure. It's designed for this, Dr. Sorensen said, reviewing the spectroscopy. Everything about this surface is optimized for controlled solar heating. Dr. Reinhardt tracked rotation period changes. Prior to perihelion, the object's rotation had been slowing, angular momentum decreasing as internal mass redistributed. At perihelion, the deceleration accelerated. By November 9th, the rotation period had lengthened to 12.3 hours, nearly an hour slower than the initial measurement in late September. Mass is moving inside, Reinhardt explained. Probably liquid water shifting under rotation and gravity. The object is thermally active at depths we can't directly observe. Photometric monitoring revealed another change. The light curve, brightness variations as the object rotated, developed a slight asymmetry. The peak brightness when the smooth hemisphere faced Earth became slightly dimmer, while the minimum brightness when the dark hemisphere faced Earth remained constant. This suggested surface modification on the bright hemisphere, either dust deposition from minor sublimation or structural changes too subtle to resolve directly. It's evolving in real time, Dr. Tanaka said, analyzing the light curve data. The surface we see today is not the surface we saw last month. On November 10th, Hubble captured post-perihelion imaging. The images showed the same hemispheric dichotomy, the same linear features, but with one new detail: a faint diffuse halo around the object, extending several hundred kilometers. Not a coma in the traditional sense, no tail, no organized structure, but evidence of minimal outgassing. Dr. Mora calculated the mass loss rate based on the halo's brightness. Approximately 0.2 kilograms per second, negligible for a 400-meter object with an estimated mass of 50 million kilograms. At this rate, the object would lose less than 0.1% of its mass during the entire solar passage. For comparison, typical comets lose 1 to 10% of their mass at perihelion. It's barely sublimating, Mora said. The coating is working. The question remained: working naturally or by design? On November 11th, Dr. Singh's SETI team completed a comprehensive radio analysis covering the perihelion period. They searched for signal modulation, time variability, frequency drift, any indication that the narrowband absorption features changed during solar heating. The features remained constant. Whatever's producing those radio dips, it's stable, Singh reported. Solar heating didn't activate it, deactivate it, or change it. It just is. Dr. Reinhardt found this troubling. If it's natural, like ionized gas or plasma interactions, we'd expect changes as solar wind intensity varied. But it's not changing. It's like the radio properties are intrinsic, not responsive. Which suggests, Dr. Mora asked. Structure, Reinhardt said. Not gas, not plasma. Something solid, stable, embedded in the object. On November 13th, a team at Caltech published an analysis of 3N Atlas's post-perihelion trajectory. Using astrometric positions measured through November 12th, they calculated gravitational parameters and tested for non-gravitational accelerations, the kind produced by comet outgassing acting as tiny rocket thrusters. Oumuamua had exhibited non-gravitational acceleration, attributed to sublimation, even though no coma was observed. The acceleration had been controversial, cited by some as evidence of artificial propulsion. 3 Atlas showed no non-gravitational acceleration. The trajectory matched gravitational predictions within measurement error. If outgassing was occurring, and the faint halo suggested it was, the mass loss was too symmetric, too controlled to produce measurable thrust. This object is perfectly balanced, said Dr. Marcus Chen, lead author of the Caltech study. Outgassing, if present, is isotropic, equal in all directions, or concentrated at the rotation poles where it produces no net torque. Either way, the result is gravitational motion. pure, predictable Newtonian. Dr. Mora noted the irony. Oumuamua's non-gravitational acceleration had fueled speculation about artificial propulsion. 3 Atlas's lack of acceleration, despite being closer to the Sun and warmer, was equally unusual. Different anomalies. Same questions, she said. On November 14th, Dr. Nakamura projected the object's future thermal evolution. As 3I Atlas receded from the Sun, surface temperatures would drop rapidly. Within 2 weeks, the bright hemisphere would return to cryogenic conditions, below 150 degrees Celsius. Within a month, subsurface temperatures would fall below freezing. Any liquid water currently present would refreeze, locking whatever processes were occurring back into dormancy. This was a thermal event, Nakamura explained. A brief window when the object was warm enough for liquid water, chemical reactions, maybe even mechanical activity. Now it's closing. And we don't know what happened inside, Dr. Mora said. No, we observed the surface. The interior remains inaccessible. On November 15th, Dr. Mora compiled a perihelion summary, distributed to the observational team, and uploaded as a preprint. The summary described surface survival, minimal mass loss, rotation period changes, and the absence of non-gravitational acceleration. The conclusions were cautious. 3 Atlas survived perihelion passage with structural integrity intact and minimal volatile loss. The thermal behavior is consistent with effective insulation and controlled heat distribution. Natural explanations involving protective crusts remain plausible, though the efficiency of thermal management is statistically unusual. The final paragraph read, "As 3I Atlas recedes, observation opportunities will diminish. The object will return to interstellar conditions, preserving or concealing whatever processes occurred during its brief encounter with solar heating. This may be our only opportunity to observe an interstellar object under thermal stress. What we learned and what we missed will shape our understanding for decades." The summary was downloaded 15,000 times in the first day. On November 16th, as 3A Atlas crossed 1.1 astronomical units from the Sun, Dr. Tanaka captured a final high-resolution image using Keck's adaptive optics system. The image showed the object as a faint elongated smudge, the dual hemispheres barely distinguishable, the linear features invisible at the edge of detection. It was the last clear view. Weather was deteriorating, the object was fading, and telescope time was shifting to other targets. Dr. Tanaka stared at the image for a long time. "What are you?" she whispered. The image did not answer. 3 Atlas had survived the crossing, the passage through fire, the thermal test, the moment when heat should have destroyed what cold had preserved. Instead, heat had transformed it. Melted subsurface ice, activated interior processes, perhaps accomplished whatever purpose the trajectory had been designed, or evolved, to achieve. And now it was leaving, cooling, returning to the dark. We had witnessed something extraordinary, but we had not understood it. What survives the crossing is not always what you expect. Sometimes it's the mysteries that endure. Chapter 14. November 15th, 2025. The shape of the question. The observation window was closing. By November 15th, 3 Atlas had receded to 1.2 astronomical units from the Sun, farther than Earth's orbit, moving outward at 31 kilometers per second. Each day, it grew fainter, colder, more distant. Ground-based telescopes struggled to track it. Adaptive optics systems could no longer resolve surface features. Spectroscopy required longer exposures, accumulating noise alongside signal. The object was slipping away. Dr. Mora scheduled a final team meeting on November 17th. The agenda: compile findings, draft comprehensive publications, and decide what to say publicly. 12 researchers joined the video call. Astronomers, geochemists, thermal modelers, orbital dynamicists. They had spent 2 months observing, analyzing, debating. They had generated terabytes of data, dozens of preprints, and more questions than answers. Let's start with what we know for certain, Dr. Mora said, opening the meeting. Dr. Tanaka summarized the observations. 3A Atlas is an interstellar object, approximately 400 meters in diameter, traveling on a hyperbolic trajectory. It exhibits hemispheric dichotomy, one eroded hemisphere, one pristine. Surface composition includes both cryogenic volatiles and high-temperature minerals. It shows subsurface thermal activity, minimal outgassing, stable rotation with measurable deceleration, and narrowband radio absorption features. What we don't know, Dr. Nakamura added, is why any of this happened. Dr. Reinhardt presented trajectory analysis. The path through the solar system is consistent with optimized solar thermal processing, maximizing heating while minimizing gravitational disruption. The probability of this occurring naturally is roughly 1 in 800. Dr. Sorensen presented chemistry. The coexistence of cryogenic and high-temperature minerals is inconsistent with equilibrium thermodynamics. No known natural process produces this assemblage. Probability of natural occurrence, less than 1 in 20,000. Dr. Singh presented radio analysis. The absorption features are narrowband, harmonically related, and rotationally modulated. They do not match molecular transitions or plasma physics. Natural explanation probability, less than 1 in 500. Dr. Mora displayed the cumulative assessment. 14 independent anomalies, collective probability below 1 in 100 billion. So we're agreed, she said. This object is statistically unusual. Unusual, yes, Dr. Nakamura replied. Artificial? That's a different claim. What would convince you? Dr. Reinhardt asked. Nakamura thought carefully. Direct detection of materials that cannot form naturally. Artificial isotopes, technetium, plutonium. Organized structures, antennas, conduits, machinery. Active systems, power generation, propulsion, transmission. We haven't detected any of that, Dr. Mora said. Exactly. So while the object is anomalous, it's not definitively artificial. Dr. Tanaka offered a counterpoint. But absence of evidence isn't evidence of absence. We're observing from 150 million kilometers with instruments designed for other purposes. If 3I Atlas is technology, automated, dormant, millions of years old, we might not recognize it. Especially if it's coated in natural material, thermally inactive, or designed not to be obvious. That's unfalsifiable, Nakamura said. If every anomaly can be explained as hidden technology, the hypothesis becomes unstable. But if every anomaly requires a new natural process we've never observed before, Reinhardt countered, isn't that equally unfalsifiable? The debate was philosophical, touching the boundary between science and speculation. Dr. Mora steered the conversation back. We can't prove artificial origin. We also can't prove natural origin. So what do we conclude? Dr. Sorensen suggested, we conclude that 3I Atlas challenges existing models of cometary evolution and interstellar object formation. We present the data, quantify the anomalies, and recommend follow-up observations if the opportunity arises. And we acknowledge the artificial hypothesis, Dr. Singh added. Not as proven, but as statistically non-negligible. We say, natural explanations remain more probable, but technological origin cannot be excluded based on current data. Will the community accept that? Dr. Tanaka asked. Some will, Dr. Mora said. Others won't, but it's the truth. On November 19th, the team submitted a comprehensive paper to Science, 3 Atlas, a systematic assessment of anomalies in an interstellar visitor. The paper presented all observations, statistical analyses, and model comparisons. The discussion section included a subsection titled Non-Natural Hypotheses, which carefully outlined how technological origin could explain the cumulative anomalies while emphasizing that such hypotheses required independent confirmation. The abstract concluded, 3 Atlas represents either a rare natural object formed under conditions we do not yet understand, or an artifact modified by processes we cannot yet identify. Distinguishing these possibilities requires capabilities beyond current observational infrastructure. But it shows peer review would take months. By the time the paper published, 3 Atlas would be beyond Neptune, unreachable, gone. On November 21st, Dr. Mora gave a public lecture at the European Southern Observatory, titled Interstellar Visitors and the Limits of Knowledge. The lecture summarized the 3I Atlas campaign, explained the anomalies, and reflected on what we learned. Near the end, she addressed the artificial hypothesis directly. People ask me, do you think it's alien technology? My answer is, I don't know. And that's not evasion. It's honesty. Science progresses by reducing uncertainty. But some questions remain open longer than we'd like. 3 Atlas is one of them. What I do know is this: we live in a universe capable of surprises, natural processes we've never witnessed, phenomena we haven't imagined, and yes, possibly, technologies from civilizations we haven't met. Our responsibility is not to jump to conclusions, but to remain open to evidence, to observe carefully, analyze rigorously, and admit when we don't have answers. 3I Atlas asked us questions we couldn't answer. That's not failure. That's the frontier. The lecture was recorded and posted online. It received 200,000 views in the first week. On November 25th, Dr. Reinhardt ran a final trajectory projection. By December 2025, 3 Atlas would cross Neptune's orbit. By mid-2026, it would pass beyond the Kuiper belt. By 2030, it would be farther from the Sun than Voyager 1, returning to the interstellar medium. In 50,000 years, it might pass near another star. In 1,000,000 years, it could cross another planetary system. And if it carried instruments, cameras, sensors, memory banks, it might record those encounters, just as it recorded ours. We were a data point, Reinhardt said during a late-night conversation with Dr. Mora. A star it visited. A system it measured. Whatever it is, wherever it's going, we're part of its record now. Do you think it's a probe? Mora asked. Reinhardt hesitated. I think it's possible. Not certain, not proven, but possible. And that changes everything. On November 28th, Dr. Tanaka uploaded a final image to the team's shared archive. The image, captured on November 26th, using Keck Observatory, showed 3I Atlas as a faint point of light against the stellar background, magnitude 23.1, near the limit of detectability. She added a caption, "Last light, clear skies, 3 Atlas, wherever you're going." On December 1st, observational campaigns formally ended. The object was too faint, too distant, and too low priority to justify further telescope time. Data analysis would continue for months, but new observations ceased. 3 Atlas faded into the noise, indistinguishable from background stars, invisible to all but the most powerful instruments, which were pointed elsewhere toward galaxies and exoplanets and phenomena deemed more urgent. The questions remained. Cold had preserved it. Heat had shaped it. And we had witnessed both, briefly, inadequately, but unmistakably. Dr. Mora wrote a personal reflection, shared only with the core team, never published. We observed something extraordinary. We don't know what it was. That ignorance will haunt me. But here's what I take from this. The universe is not obligated to be comprehensible. It doesn't owe us answers. Every measurement we make, every spectrum we capture, every model we build, these are acts of hope. Hope that the cosmos can be understood, that patterns exist, that knowledge is possible. 3I Atlas challenged that hope. It showed us limits, instrumental, analytical, conceptual. We could see but not touch, measure but not sample, speculate but not confirm. Maybe it was natural, a comet formed in conditions so rare we've never seen them before. Maybe it was artificial, a probe sent by minds we cannot imagine, for purposes we cannot guess. Or maybe the distinction is false. Maybe the universe contains phenomena that blur the line between natural and designed, between evolved and engineered. I don't know. But I know this. 3 Atlas came from cold. It endured heat. And it survived both, carrying its secrets back into darkness. We were not ready for it. Maybe we'll be ready next time. Or maybe the next one won't wait for us either. Nyon, done? On December 15th, the final observational dataset was archived and made publicly available through international data repositories. Terabytes of spectra, images, thermal maps, and radio observations, free for anyone to analyze, reinterpret, or challenge. The data would outlive the object's visibility. Future astronomers, with better models and deeper understanding, might find answers the current generation missed, or they might find deeper mysteries. On December 17, 2025, Dr. Mora received an email from a graduate student in South Korea. The student had analyzed the Hubble images and noticed something subtle. The linear features on the bright hemisphere were evenly spaced, separated by intervals of approximately 47 meters. Periodic spacing. Not random. Not chaotic. Evenly spaced. Dr. Mora stared at the measurement. 47 meters. A curiously specific interval. Natural fracture patterns don't produce such regularity. Geological processes are stochastic, not periodic. But instrumentation has limits. Measurement uncertainties accumulate. Pattern recognition is prone to bias. Humans see order even in noise. She ran statistical tests. The spacing was significant at the 95% confidence level. Not definitive, but not dismissible. She opened a reply to the student. "This is interesting. Can you share your analysis?" Then she paused. Another anomaly. Another improbability. Another question. She closed the email draft and walked to her office window, staring at the night sky. Somewhere out there, beyond Neptune, beyond the Kuiper Belt, 3I Atlas was cooling. Its surface was returning to cryogenic temperatures. Subsurface water was refreezing. The thermal event was ending. And the object was leaving, carrying whatever had happened inside it, processes observed from outside, but never understood, back into the dark. The shape of the question had become clear. Not what is 3I Atlas, but what do we do when we observe something we cannot explain? Do we demand certainty before acknowledgement? Do we wait for proof before consideration? Or do we admit that the universe contains mysteries our current tools cannot resolve, and that admission itself is a form of knowledge? Dr. Mora didn't have the answer, but she knew one thing. This would not be the last interstellar visitor. Detection networks were improving. Surveys were expanding. Within a decade, we might observe dozens of interstellar objects. And if 3I Atlas was unusual, statistically anomalous, thermally sophisticated, chemically contradictory, then perhaps it represented a category we hadn't yet imagined. Not natural. Not artificial. But something else. Something shaped by processes, evolutionary, technological, or otherwise, that operate on timescales longer than civilizations and distances greater than comprehension. The universe was speaking. We had listened, but we hadn't yet learned the language. On December 20th, 2025, Dr. Mora drafted a final statement for the team's website. Observations of 3I Atlas have concluded. Analysis continues. Data is public. Questions remain. We witnessed an object shaped by extreme cold and solar heat. We measured anomalies we cannot fully explain. We explored hypotheses, natural and otherwise, that push the boundaries of planetary science. This is not science fiction. This was November 2025. And the cosmos remains full of mysteries we have only begun to explore. Stay curious. Stay rigorous. Stay open. And keep watching the sky. The statement was posted on December 21st. The same day, a new interstellar object was detected by Pan-STARRS. Designated for our 2025 X1. It was inbound from interstellar space, approaching from high ecliptic latitude, on a trajectory remarkably similar to 3I Atlas. The cycle was beginning again. And this time, we would be ready. Or we would learn once more how much we still didn't know.